Hello, everyone, and welcome. It's great to see a packed audience here today. Welcome to the AI and Machine Learning Summit. I am Michelle Lee, Vice President of the Machine Learning Solutions Lab. The mission of the Machine Learning Solutions Lab is to accelerate our customers' adoption of machine learning to solve your real-world business problems using the full panoply of AWS ML offerings. I have the privilege of being your hostess this afternoon. For the past 3 years at re:Invent, this summit has given our attendees the opportunity to hear from researchers, academics, and entrepreneurs on some of the most important and relevant topics in AI and machine learning. This afternoon, we will hear from 8 speakers on how they are using machine learning to unlock breakthroughs in medicine, to help us eat more sustainably, and to help us respond more effectively to natural disasters and more. We'll also cover pressing issues such as deep fakes and bias and ethics in machine learning. I am personally excited to hear from our lineup of speakers this afternoon. This is my first re:Invent. I joined AWS a short time ago from my former position as head of the United States Patent and Trademark Office and a Silicon Valley tech executive and AI researcher before that. When I was head of the US Patent and Trademark Office, I used, of all things, AI and data analytics to help improve the quality, consistency, and throughput of the patents the agency issued. And what I realized is that if the United States Patent and Trademark Office, a 200-plus-year-old governmental agency that traces its roots back to the founding of our country, doing the same thing for roughly 200 years, has a machine learning opportunity, so too does every company, regardless of its size, industry, or sector, public or private. That's why I'm excited to be part of the AWS machine learning team, and that's why I'm super excited to be with you here today to hear from our speakers on machine learning. We have a full agenda lined up for you this afternoon. We will begin with 4 speakers, take a 15-minute break, then continue with 4 excellent additional speakers. So, I hope you came curious, eager to learn, and ready to be inspired. And without further ado, allow me to introduce our first speaker, Rafael Gutardo at the Fred Hutchinson Cancer Research Center. He is the scientific director of the Translational Data Science Integrated Research Center. Rafael, please join us on stage. Audience, please join me in welcoming Rafael Gutardo.
Thank you so much, Michelle, for the introduction. So I believe we can cure cancer in our lifetime. And machine learning could play a very big role in that. So before we get started, let me ask you a question. How many of you know someone who's been affected by cancer? Raise your hand. Look around you. It's pretty amazing. It's actually frightening. So according to statistics, 1 in 3 people will eventually be diagnosed with cancer. 1 in 3. What if we could change these statistics? I believe that we can change it. And by we, I mean us, the FedEx, a leader in cancer research. But I also mean we, technologists in this room and beyond. So let me tell you a little bit about the FedEx before we get started. So we're a cancer center. We were founded about 40 years ago. We are actually named after a baseball player, Fred Hutchinson, who unfortunately died of cancer. Today, we have over 3,000 people who work fearlessly to prevent, treat, and ultimately cure cancer, HIV, and related diseases. We've had 3 Nobel laureates, including Dr. Thomas, pictured here, who pioneered bone marrow transplant, a form of immunotherapy. We're located in Seattle, right next to Amazon, AWS, but many other biotech and tech industry, nonprofits, academia, the University of Washington. So from bone marrow transplantation to artificial intelligence, Seattle is a global epicenter of breakthrough ideas. we've got people who are extremely talented in data science, machine learning, and other advanced technologies right in our backyard. And we've started to work with them to try to cure cancer. So let me get back to curing cancer. Here's a visual of a cancer cell being attacked by multiple T cells. So it turns out that the immune system is actually the best weapon we have against cancer. However, it doesn't work all the time. Cancer cells can be very clever. They are very good at hiding from immune surveillance. So at Fred Hutch, we've been working very hard to try to come up with new therapies called immunotherapies that are basically leveraging the immune system, try to boost, retrain, or even re-engineer someone's immune system to fight cancer cells. And we're seeing amazing results. In fact, we can already talk about cure in certain patients and certain cancer. Unfortunately, it doesn't work all the time. Some people do not respond. Others will initially respond, but then they will relapse. And so we're trying to understand why. Is that because the cancers are different? Or maybe our immune systems are different? In fact, did you know that our immune systems are highly diverse? For example, we each have around 1 billion unique T cells in our body. T cells are part of the immune system. They are very important cells that try to kill abnormal cells like cancer cells or cells that are infected by viruses or bacteria and things like that. And some of that diversity can be linked to basically the proteins that these cells express. So if you think of the protein as a little engine, the cell as a little engine, the proteins are actually all the little parts that make it work. And my T cells can be very different from yours. It turns out that sometimes the T cells that are very important, for example, the ones that will actually respond to immunotherapy, can be extremely rare. Potentially 1 in 100,000 T cells. So we need technology to not only look at T cell diversity, meaning how, what sort of proteins do a cell express, but also be able to do that in a high throughput fashion so that we can collect lots of cells and potentially go after these very rare cells that might be very important. Today we have such a technology. It's called cytometry. It's actually a single cell technology, meaning that we can actually take, let's say a blood sample with millions of cells, pass them through a machine, and the machine is going to quantify how much expression do we have for 40 to 50 proteins. It's very fast. We can actually do that in a matter of minutes. One sample, millions of cells, 40 to 50 proteins. For those of you who think in terms of arrays or matrices, you can think of it as per patient, per sample, a large matrix with millions of rows, these are your cells, and 40 to 50 proteins, these are sort of your variables. Now, if you look at these pictures, so this is the instrument that you can see on the right-hand side. On the left, this is actually the analyst that analyzes this data. And I kid you not, the standard way to analyze this data is basically to stare at a screen and try to draw circles around sort of cells that look similar to one another. So I'll show you that on the next plot. So this is an example. Let's say we're measuring 3 proteins in all of our millions of cells. So we have CD3, CD8, and then CD4. CD3 is a very important protein. It's actually how we define a T cell. So T cells are positive for CD3. So on the plot here, you can basically see the protein expression of CD3 versus CD8 on the y-axis. Each dot is a single cell, and the color actually tells you when there's lots of cells that are basically overplotting. So it's the density, so there's more cells there. So if you look at basically everything that's sort of circled there, these are your CD3 positive because they're high for CD3. And in this case, the analyst actually draws sort of an ellipse around the CD3 positive cells to define T cells, and then took these cells and looked at the other 2 dimensions that we measured, looking at the expression of CD4 versus CD8. And here we can define the CD4 positive and CD8 negative T cells, and the CD8 positive, CD4 negative T cells. These are important. They are CD8, they are called the killer T cells. These are the cells that actually kill, let's say, cancer cells. The CD4s are helper T cells. They help the immune system by producing a lot of effector molecules that actually stimulate immune responses. So the point I'm trying to make here is that this is actually the standard way we analyze data in the lab. It's manual, it's time-consuming, it's sort of subjective, it's not data-driven. More importantly, you might sort of say, well, it's fine because here we can kind of see these populations, so we can draw these circles around and we understand where they are. But we're looking at only 3 proteins here. So if you consider 3 proteins, you might sort of say, okay, I can actually do it because there's 8 different combinations. If you pick 2 markers or 2 proteins, you can plot them. You have basically 3 scatter plots. But these grows exponentially. If you have 10 proteins, potentially you have to look at thousands of scatter plots. If you have 20, you have millions of combinations. If you have 30, you have billions of combinations. So not only it doesn't scale, what's going to happen is that oftentimes the way these people will explore the data and try to look for interesting populations of cells or T cells will be very limited and biased. And so I can guarantee you that in any of these data sets, there's going to be information left on the table. And that information might actually be very important in predicting who's going to respond to immunotherapy. So because this is a machine learning conference, I thought I would sort of walk you through what we're trying to do to solve that problem. And then I'll show you applications of it. So I have a few cartoons that will try to illustrate that. So let's say we're looking at a lot of T cells. These T cells, because they are T cells, they express CD3. I told you that's how we define a T cell. So we have CD3 on the surface of these cells. And then if we were to measure CD3 by that technology called cytometry, we would basically sort of get a distribution that's all high or all positive for that protein. And you see a peak because it's not a perfect measurement. There's some variation from cell to cell, so we will express more or less of that protein. Now, if we measure other proteins, it will sort of look like this, because maybe for CD8, some cells will be positive for that protein, some will be negative. So that distribution will be bimodal. You get 2 peaks. And you don't get exact 0, because again, this is an imperfect measurement, and you get measurement error or background noise. And so you get that sort of negative peak, low intensity, high intensity, positive. So if we were to look at a T cell, let's say, that express all of these 5 proteins, they will all be on the right-hand side. So their measurement should be above that threshold positive. Now, if we look at one that's negative for CD28, it would fall on the other side, right? So you kind of get the idea. By looking at where these cells fall in terms of measured protein expression, you can sort of guess what the phenotype is. So we can actually explore the space by building sort of binary trees and deciding on what a cell is depending on the expression of certain proteins. So we can start with CD3. You can see they're all positive. Then we can look at the other marker depending on where they fall. If it's on the right, these are CD8 positive, and therefore I call them CD8 positive. If it's on the left, CD8 negative, call them CD8 negative. And then we can do that for other markers. We can look at another one called PD1. And then do the same. For the CD8 positive, we split according to where they fall, and then we call them negative or positive, and so on and so forth. These are actually cartoons, meaning that these are not real density that we actually get from the data. The density we observe are typically a little bit more noisy, so we have to make decisions as to where is the negative, where is the positive peak, so we have to use cutting-edge density estimation for doing that, and then making decisions as to whether there's actually 1 peak or 2 peak, or even more than that. Sometimes we see distributions that have 3 peaks, and this is actually very important. Sometimes there's sort of a no expression, a low expression, which we call dim expression, or a bright expression. And those actually have a lot of importance from a biological point of view. And these, we can make the decision based on the data. This is actually fully data-driven. We can decide on whether we see 1, 2, 3, or 4 peaks. Now, the order kind of matters. So here I started with CD3, then looked at CD8, and then PD1, but we could have done, CD3, PD1, CD8. There's a lot of different combinations. So we actually looked at all these combinations. So we actually built what we call an annotation forest. We're doing a forest of trees. We're going to look at all the different combinations and the order we can look at. This is important for a couple of reasons. One, because the order might matter, and so we want to know that. But more importantly, because there's actually structure that might not be apparent right away, but if you sort of look further down in a tree, once you've conditioned on things, you might sort of see some structure. So here's an example. Let's say I'm, again, looking at some T cells, and I'm measuring another protein, and I want to know whether my cells express or do not express these. But the distribution looks like this. So there's no clear separation between what's positive or what's negative. Now, if I were to look at maybe CD8 first, once I remove the CD8 negative cells, and I just look at the CD8 positive, maybe I see structure. The idea there is that maybe there's lots of cells that don't actually express a certain protein, and so you should actually use that for deciding what's positive or negative. So this is very helpful for doing that. Now, I've told you we looked at all the trees. We built a forest, but I lied a little bit. We actually do that, but we only look at combinations of 4 proteins. Because if we're to look at more than 4, again, it grows exponentially. We can't really do that. Even a computer cannot sort of cycle through billions of different things. So we have to be a little bit more clever. So we stop at 4 just for deciding what are the thresholds and what do we call positive, negative. Then we're still going to build the giant forest with the very long trees. We're going to look at all the different combinations. But we're not going to do that for all the trees. We're just going to randomly sample a large number of trees, let's say 1,000 trees, and we're going to look at all these combinations. And here what I'm showing you is very similar to classification trees, for those of you who know. And when we sample these trees, it's similar to boosting or bagging. And the idea there is that we want to look at all these trees, and what's going to happen is that when we build all these trees, you're going to get different paths that lead you to maybe the same T cell subset or the same phenotype. For example, here, you know that the cells will be basically blue and then yellow and then sort of dark blue and pink and green and orange. And you can see I have many ways to arrive at that combination of proteins. Maybe some of these ways give me better populations. And the way we define better is basically if you think of the data in a sort of large, high-dimensional space, you can think of spheres. We want something that's more spherical, that looks a little bit more like a population we trust. So basically, we do all these trees, and then we're only going to collect the populations that are unique and that we think are relevant. So we're kind of doing variable selection, and we're looking at the quality of these populations. And this is important again. So these led us to build an algorithm that we call FAST for fully annotated shape-constrained trees for looking at these combinations of proteins for defining populations. What's important here is that it is an interpretable machine learning. So we basically build it by knowing what the experiment is, what the data look like, what it means in terms of the biology. What that means is that at the end, we actually get a phenotype or a label for the populations of interest that tells you exactly what these cells are. For example, they will tell you, here's a population of cells, of T cells. These are CD3 positive, CD4 negative, CD8 positive, PD1D. And that's very important because if you're a biologist, you want to know what these cells are. It's also important because if we actually analyze data where we're going to take a blood sample, guess what? We don't just analyze a single blood sample. Typically, we're going to have multiple blood samples from a patient over time or maybe from multiple patients across a clinical trial. So we need to be able to compare these data. And if you think about this problem as a clustering problem where we're trying to identify sort of populations of cells, you might sort of run it per sample, but you're never really going to know what these are. And so if you have a population and then you want to compare it to maybe after treatment, you don't know what those are. So you don't know which one corresponds to which. Because here we have a label, we can do that. And this is a big advantage compared to state-of-the-art algorithms. So one of the things that we had to work with is how do we scale? I told you that we're doing all these sort of exhaustive partitioning, we're doing all these trees and building these forests, and that's pretty computationally intensive. So we had to think a lot about how do we scale? How do we analyze large clinical trial data sets? Because we're going to have millions of cells, hundreds to thousands of samples that we're going to be analyzing. And so we basically use AWS batch using tools such as Nextflow and Docker for basically trying to parallelize some of these computations because we can do it on a per sample basis. So we can basically scatter all the computation, gather the results, compute what we need, and then scatter again and gather again. So this is really a nice way for doing the computation. Okay, so let me get back to the science. Why is this important? So here's basically, we've been working on a cancer type called Merkel cell carcinoma. And we have a world expert at the Fred Hutch we've been working with, Paul Niem, who exclusively work on this cancer. So this is a very aggressive skin cancer. It's actually twice as likely to metastasize as melanoma. And up until recently, with the advance in immunotherapy, there was basically no treatment for it. So basically, the survival rate after chemotherapy, after 3 years, was only 10%. But now we have new drugs. And with immunotherapy, so a drug called pembrolizumab, we're already seeing amazing results. So this is a patient that had this cancer, and we're seeing the pre-treatment. So you can see there's a lesion that's basically circled in black. And after treatment, it's completely gone. All you can see is a little bit of scarring. What's amazing, it took only 3 weeks, and it's 1 dose. Basically, this treatment is actually boosting your immune system. All it's doing is basically reactivating these T cells, and they go about, find the cancer cells, and kill the cancer cells. Amazing, amazing results. But guess what? It doesn't work in everybody. And even among people who respond, some will relapse. In fact, this patient was in complete remission for 3 years and eventually relapsed. So if you look actually at the FDA announcement when the drug was released, there was some statistics in there. The response rate was between 50 and 60%. The complete response rate was only about 25%. So if you think about curing cancer, this is great because we have a drug now that's approved for treating Merkel cell, but it's not anywhere near we want it to be. So the question we're asking is that if you think about, let's say we're taking 4 people, and only one of these out of these 4 will have a complete response, what's different about this patient? What can we do to learn that will improve immunotherapies, that will help us make the new immunotherapy that eventually will lead us to 100% response rate? So that's kind of the idea here. So being at the Fred Hutch, again, we had the opportunity to work with the folks who were involved in the clinical trial that actually led to the approval of that drug. And by the way, this is a drug that led to the 2018 Nobel Prize in Medicine because this was such an important discovery for cancer treatment. So we had the opportunity to basically have access to some of the data that were collected through the clinical trial. Basically, we had 27 subjects, 18 of which responded to therapy. And they had collected these sort of T-cell data using the cytometry platform. And so we were really interested in using a new approach to try to reanalyze this data, looking at, maybe there's some flavors of T-cells that may be sort of correlated with clinical response. And we went to our collaborator and we said, we want to work with you, we'd love to reanalyze this data. And they said, this is amazing, we really want to work with you, but they say, just to let you know, there's no signal in these data, we've looked at it. So we went ahead anyway and we reanalyzed this data. We actually identify between 200 and 300 different distinct T-cell populations in these patients. And then for each of these populations, we compared basically the frequency of these T-cells between the responders and the non-responders. And I should say that these are actually data prior to receiving the drug. So this is prior to immunotherapy. So this is basically looking at the state of the immune system before they receive the drug. And among these 200 populations, we had 2 that were strongly different between the responders and non-responders. And so we were really, quite positive when we saw that because we identified something that discriminated between these responders and non-responders. And then what the algorithm tells us, remember, not only it gives you population, but it will tell you what the cells are. And these are the labels that you can see. So for those of you who are not really biologists, basically it's saying the first population, by the way, these are box plots looking at the frequency. So the y-axis is the frequency of these T cells in the blood, broken down by responder light blue and non-responder dark blue. So what you see is that the responder have more of these T cells. So the one who responds to the drug have more of these T cells before receiving the drug. On the left-hand side, I'm going to read this. It says that these are CD8 positive, CD3 positive. So CD3 positive, they're T cells. They're CD8 positive, meaning they're killer T cells. And they express PD-1. And PD-1 is actually what the drug is targeting. So PD-1, you can think of it as sort of an on-off switch on these T cells. When PD-1 is expressed, the cell is off. It can't really act. When PD-1 is not expressed, the cell is activated and it can kill cancer cells. And cancer cells are actually very good at turning that switch off so that the T cells are not going to attack them. By blocking that switch, we basically prevent the cancer cell from manipulating the switch, and we're basically releasing the brake so that the T cell can attack the cancer cells. And so what we're finding is, guess what? If you have more of these T cells to begin with before you receive treatment, and we give you treatment that actually acts on these T cells, then you're responding better. Makes a lot of sense because you had those, the drug is acting on these cells, and you're responding better. So, and on the right-hand side is basically the same phenotype, but these are the helper T cells that are also important because they stimulate the immune response. So at this point, you might sort of ask, but why did they miss that information? Because that's kind of known biology. They should have looked at this. And they did, but they never looked at that combination. So PD-1 alone, so just looking at these T cells that express PD-1 is not enough. You need to look at PD-1 expression with CD28, which is another very important molecule, and HLA-DR, which means that they are activated. So they've never looked at that combination. And so by using an algorithm that knew nothing about the drug, that knew nothing about treatment, we drilled down to something that was actually very important from the point of view of the biology. And one thing that we know about these cancers is that if you get a tumor biopsy, and if you look at what's in the tumor, actually the frequency of T cells that express PD-1 there in the tumor is actually a predictor of response. So that we know from the tumor, but we've never seen that from measuring it in the blood, presumably because it's actually pretty hard to measure because these are extremely rare, and any method's going to miss them, but machine learning picked that up. And our data actually correlates with what's measuring in the tumor, so we believe that this is true, because it actually recapitulates the gold standard, which is measured in the tumor. But measuring things in the tumor is actually very hard. Typically, it's a lot easier to get a blood sample and to look at blood. And in fact, for some cancer types, we don't even get tumor biopsies, so we can redo that in the tumor. So now, being sort of a computational scientist, we say this is great, but what we love to do is validation. Can we get another data set where maybe we can validate that signature and see if this is real? Do we really see this sort of strong predictor among other maybe clinical trials? And so we're actually doing that validation internally, looking at the exact same port, generating more data. But, because this is science, this is academia, there's a lot of things that are being published, we went ahead and looked for papers that looked at similar studies. And we found one that looked at actually the exact same drug in melanoma, which is different skin cancer, but it's still a skin cancer. And so we figured that maybe there's something common there. We could look at these data. And also the data were available, which is not always the case, but I think it really shows the power of open data in this case. We're able to look at this paper, go into the data, reanalyze the data, because they had used a very similar technology, not exactly the same, but thankfully for us, they had the exact same markers that we had in our sort of cytometry data set. So we can actually extract the same population. And we did, and guess what? It correlated. The exact same phenotype also predicted response to anti-PD-1 therapy in melanoma. So what are we going to do with this information? So what if we could move, I told you our goal is not to get 25 to 50% response rate, it's really to get to 100%. So the first thing we can do is we know the patients who are more likely to respond to therapy now, so we can probably come up with a good biomarker, maybe sort of a diagnostic biomarker that will allow us to maybe target the drug to the right patients. Why do you want to do that? Because these patients, they have a timeline and they're counting for their life. And so if we can sort of give them the right therapy from the get-go and avoid giving them a drug that's not going to work, that potentially has a lot of side effects, that's something we want to do. We don't want to give somebody a drug that's not going to work. So we can do that. And basically, we can increase the response rate by targeting the drug to the right patient population. But the other thing we're very interested in doing is not only doing that, but maybe can we learn from this and come up with a new drug, a combination of drug that will maybe enhance what we're seeing, maybe, for example, modulate the immune system so that we can increase the frequency of our sort of PD-1 positive T cells to begin with, so that when we give the drug, boom, it works. So we do think there's ways we can actually manipulate the immune system or potentially re-engineer the cells to come up with new strategies. So that's really what we're after. And going back to the story I told you earlier, so, at the Fred Hutch, we pioneered bone marrow transplantation. Did we do that overnight? No, it took a lot of time. Basically, it was a lot of, trial and failures. And we, meaning Dr. Thomas, ran a lot of different clinical trials in trying to understand how does that work. When you do a bone marrow transplant, what's the right way to do it? To begin with, at first, we did not really understand that, you had to match the patient, right? Because there's sort of a genetic component that if you don't really match the right genetic, then you might sort of reject or you might not have a good engraftment of that bone marrow transplant. So this was very important, and we learned that from data that were generated from these clinical trials. The other thing that we learned through this is that at first we thought that when somebody has cancer, what we're going to do is that we're going to give them a bone marrow transplant so that we're going to basically get rid of all the cancer cells and replace them with healthy cells. It turns out that's not really how it works. That's partly how it works. But when you get a transplant, what happens is that the donor also has some very healthy T cells. And guess what? These T cells help killing cancer cells. So they basically help keep the cancer in check. They get rid of all the residual disease that the patient has. And with this therapy, we actually went from basically 10% response rate initially to 50%. And here we're really talking about cures, because these patients, they fail chemotherapy, they're getting a bone marrow transplant, and in many cases, they go on to live normal life after that, or close to normal. And this is really amazing, and that's a curative therapy. So at FedHutch, we're now thinking about how can we do that with immunotherapy. And we are very lucky to have something that's called the Bezos Family Immunotherapy Clinic, where we have a great facility where we're seeing patients, we're giving them the best-in-class drugs, the new clinical trials, also products that are not commercialized. What this means is that we have access to a lot of samples that oftentimes are eager to participate in research. And we have built the best way to collect samples and generate massive data sets from the patients that we're seeing. And from that, we are currently thinking about building the largest database that we can of immunotherapy data sets that are generated from the patients that we're treating at the clinic there. And our goal is then to use machine learning and AI to extract new insight that will move us closer to that 100% response rate and to our goal of curing cancer. So the future of cancer research has just started. I invite all of you to visit this webpage. There's many ways you can participate and you can be part of this revolution. Thank you very much.
Thank you. Thank you, Raphael, for that excellent talk. Our next speaker, speaker number 2, is Cornelia Caraja. She is from the University of Chicago, where she is the associate professor in the science and engineering offices in the computer science department. Please join me in welcoming Cornelia Caraja.
For being here. I'm very excited to talk about deep learning techniques for disaster management and response. So there are many disasters that happened in recent years, in the last 5 to 10 years. And these disasters are not only deadly, but also very costly. For example, these are some of the disasters that happened in 2017, and they cost billions of dollars. And so we study disasters, and we pursue research in to increase disaster response and communication using social networking sites. Social networking sites connect people all around the world, and have become part of our daily lives and everyday communication patterns. We focus on Twitter as there is large amount of tweets that are posted, and there are also millions of active users that are monthly active users. So as the use of social media is on the rise, so is the use of social media in disaster events. And the affected populations have become the source of big disaster data. This is an example from the Hurricane Sandy. The number of tweets that are posted per day as the disaster progressed, the Sandy hurricane progressed. And as we can see here, in the days when the hurricane hit the East Coast, there were millions of tweets that were posted in Twitter. This is another example from Tohoku earthquake from 2011. And the edges here, the blue and white edges, show the huge number of tweets that were posted, that were in and out of Japan as the earthquake hit. Social media is very important in disaster events, and researchers assert that bystanders on the ground are uniquely positioned to share information that may not yet be available anywhere else in the information space. So microblogging data from crowds of non-professional participants, from the people on the ground during disasters, is seen as being of significant value. Social media has made the headlines of many news articles as well. For example, the Wall Street Journal, one of the headlines says, Hurricane Harvey victims turn to social media for assistance. There are still challenges with using social media in disaster events. So despite the huge value, and despite the fact that scholars of disasters see significant value in Twitter data that is posted during disasters, there is still very little uptake very little uptake of message data by response organizations, by large-scale response organizations. And one of the potential reasons for doing this is that response organizations operate under extreme conditions of extreme uncertainty. And another reason is that with the exponential increase in social media data, so it comes the increase in irrelevant data. So how can we identify useful content in Twitter? One potential way is to use a direct Twitter search, for example, a keyword-based search, like searching for Oklahoma tornado, or Oklahoma or tornado, or hashtag Oklahoma tornado, if we are interested in tweets that are posted during the Oklahoma tornado. Another approach is to use a location-based search. So that would be to collect all the tweets that contain geographical coordinates inside the affected areas. However, this will retrieve lots of irrelevant tweets. And an example of such irrelevant tweet is the following. I lived in Oklahoma since I was born. So this contains the keyword Oklahoma, but has nothing to do with the Oklahoma tornado. On the other hand, a manual selection, a manual approach, is very time-consuming, and hence, there is an increasing need to automatically extract appropriate information, which could lead to improvements in the response process. So our questions were, in a social media stream of messages, what is the useful information to be extracted from the tweets, and that useful information to help emergency response organizations as well as people on the ground to become more situationally aware during and after a disaster. And what are the best models that can help to automatically identify messages that are useful during disasters and can help us extract the relevant information from these messages? There are several classes of machine learning algorithms. One of them is to use a supervised learning approach, have lots of labeled tweets to train reliable models, and then use those models on incoming tweets. However, this is not quite possible when a disaster happens because the data, so users are posting messages, and these messages are not labeled. So these messages so we don't have labeled data to train reliable machine learning models when a disaster just starts to unfold. So we proposed domain adaptation techniques precisely to use data from previous disasters for which we have large amounts of labeled data together with unlabeled tweets from the disaster that is just unfolding. This is our framework that we designed. So as the disaster starts unfolding and the affected population starts posting messages on social networking sites, the data is streamed, crisis data is streamed, and then together with historical crisis data and models that we store in a repository, we build deep learning techniques, and then so that will create us label data that can be validated with use of crowdsourcing volunteers and possibly fed back together with historical crisis data to refine our models now using data that is labeled by humans from previous disasters together with data that is labeled by the deep learning models and portions of the data that are validated using crowdsourcing volunteers. And so the refined models will make predictions, further predictions on the incoming tweets, which will help build better decision models for response organizations. So in our framework, we use first the Twitter streaming API to crawl tweets posted during crisis events. We parse the tweets to extract the text, the hashtags, media information, user information whenever available, and the geolocation also whenever available. And then we perform text classification, natural language processing, and text analytics on the tweet text. In the pipeline, as we stream the tweets, our data, the first thing is to have a classifier that will identify information that would identify if the tweets are relevant to the disaster or not. Then the next step is to identify if the tweets are posted by eyewitnesses. Then if the information, if the tweets would contain information that would convey any type of information that would help increase situational awareness. And then identify situational awareness categories such as damages, injured people, missing people, and so on. Here are some examples of informative tweets, tweets that convey examples of actually both informative and not informative tweets. Tweets that convey some information, and tweets that are just type of chitty chat, non-informative. And so an example of informative tweet is the following. More than 765,000 homes in 7 states have no electricity, with New York and New Jersey being most affected. So this would increase our situational awareness and preparedness for the disaster. And a non-informative tweet looks like this Hurricane Sandy. Twitter is so annoying. We studied the effectiveness of deep neural networks in comparison with traditional machine learning classifiers for identifying informative messages from social media streams. And so we designed strong baselines using the traditional machine learning and particularly the knife-based classifiers. We designed hand-engineered features extracted from the tweet content, denoted as TC, user features, denoted as UF, and polarity features. We also use the bag of words, the tweet content, and the combinations of these features together. And we use these features in conjunction with the knife-based classifiers. In addition, we trained deep neural networks, particularly convolutional neural networks and recurrent neural networks, and found that using CNNs, convolutional neural networks, performs best with performance on identifying informational tweets reaching about 95% in F1 measure. We did this on both natural and non-natural disasters, man-made. And we also did across domains, training on natural disasters and testing on non-natural disasters. The next thing that we focused on was identifying situational awareness categories. And for this, we actually formulated the task as an information extraction, particularly extracting or recommending hashtags that will contain situational awareness categories, such as damage, injured people, needing help, and so on. We looked at some of the tweets from our collection of data, and we found that some of them have no hashtags at all. Some of them have just the right amount of hashtags so that these tweets can be easily retrieved. And we also found that some of the tweets will have a lot of hashtags, and some of them may be just variations like grammatical inflections of words. So we also annotated the tweets so that the hashtags that are shown in blue color are the hashtags that were user annotated. We annotated these tweets using Amazon Mechanical Turk. And we also created a disaster lexicon for the annotations. And so, for example, for the first tweet, we need help in Houston. Our apartments are surrounded with water like an island. We need rescue at this address. So this tweet had no hashtags available. And so the annotators, Amazon Mechanical Turk annotators, annotated this with need help, Houston, and need rescue. And so the hashtags or the words, phrases shown in red are the ones that are our gold standard for evaluation, and the ones that were annotated with Amazon Mechanical Turk. And for this task, so we formulated it as a sequence labeling task and used a variant of recurrent neural networks, which is called long short-term memory networks, LSTM. And they're variants that take into account the informal writing from social networking sites. And so our models, so we used a large collection of disasters to train our models. So we had in our repository of historical crisis data, we had data collected from about 30 disasters. And we used 4 test sets for evaluation: Hurricane Maria, California fire, Philippines flooding, and then the last test set was from multiple disasters, collection from multiple disasters. And so here, as we can see, we reached performance in the 90s in terms of the F1 score. We also look to see how our models perform, to do an anecdotal evidence, to see how well the models perform. And so the blue, the words that are highlighted in blue are the ones for which the models agreed with the gold standard. The words that are highlighted with yellow are the ones where, so these are the gold standard, but the model did not identify them as hashtags or keywords. And then the ones that are shown in red are the ones that are identified as keywords or hashtag by our models, but were not part of the gold standard. And we were quite excited to see that the models perform very well on most of the tweets, and there was a huge agreement between the predictions and the annotators, the gold standard. Then, so for the part that I mentioned on the eyewitness, the tweets that are posted by eyewitnesses, most often we don't have the geolocation available for the tweets. And we used locations. We identified the locations using the Amazon Comprehend to track a hurricane path, so this can be integrated into our model to further improve the performance. And so on the right side, we can see the Harvey hurricane's real path. And on the left-hand side, we see the Hurricane Harvey's predicted path using the Amazon Comprehend And as we can see here, the two paths almost coincide. So that is quite accurate performance on predicting the locations, identifying the locations of tweets, and how the hurricane progressed over the years, over the days, as the disaster unfolded. I would like to thank the students who participated in this research, Kishore Nepali, Jisnurey Chaudhuri, Brandon Trong, Honming Lee, and collaborators, Doina Karaja, Andrea Tapia, and Kash Parker. And I would also like to thank NSF for funding this research, as well as AWS for support, and particularly Sanjay Paddy for his continuous support on this project. And thank you very much.
Thank you very much, Cornelia. What a wonderful use of machine learning. Our third speaker of today is Guido Joret. Guido is the Chief Digital Officer from ABB. Please join me in welcoming Guido.
Thank you, Michelle. Thank you very much. So you've heard two very different presentations already today. Allow me to introduce a third. And I feel a little bit like I'm carrying coals to Newcastle, as they say in the UK. I'm telling you why AI will drive the industrial world, the Internet of Things, to the cloud. Of course, this is a whole cloud conference, so it seems like we're stating the obvious. But let me bring you a little bit into my world. I work for a company called ABB, and it's not Airbnb, it's a Swiss industrial company where we make robots, we make electrical gear, transformers, motors, and we've been around for 130 years. And we are witnessing some of the biggest changes happening to our world that we've ever seen. And some of you have probably heard about the fourth industrial revolution. Let me back it up a little bit and explain how we got here. So in the beginning, we used muscle, we used brawn, and in 1784, the steam engine was invented, and it allowed us to dramatically increase the amount of power we could deploy by using steam. That was the first industrial revolution. That unleashed a whole bevy of productivity in terms of factories, mass producing goods and materials. And then in 1870, and our company was quite instrumental in this, we introduced electricity. And a steam engine was really powerful, but it was also very big. Electric motors are small, and you can deploy them more widely in many more places. That was the second industrial revolution. And some people think that the fourth industrial revolution is all about the advent of computing. But actually, we've had computing in the industrial world in terms of programmable logic controllers, embedded systems, SCADA environments, industrial PCs, for quite a while, actually going back to the late 1960s. So what's different with the third industrial revolution, which was really the advent of automation, digital technology, controlling the electrical systems, controlling the mechanical environments, and this fourth industrial revolution? And I think primarily it's because we're moving from systems that can act and react to systems that can plan and learn. The introduction of software-defined capabilities driven by the cloud. And the transformation that this is engendering cannot be overestimated. It's changing the way we produce goods in factories, it's changing the way we do transportation, and it's also changing the way we produce energy. And this progress over about 250 years has dramatically changed how all of us live. but it has come at an incredible cost. The benefit is that if you go back to when the steam engine was invented, average life expectancy was 37 years old. Today, we enjoy life expectancies in most of the world that's double that, if not more. But we have a problem. And I call this problem iOS. And no, it's not version 13.2, although I have some problems with that too. But it's about the industrial operating system. It's the way in which we provide energy, food, water, transportation. Because in the industrial way, we achieved tremendous gains in productivity through centralization and making things very, very large. Large power plants, highly centralized, big farms, big manufacturing plants, gigafactories, but the future will not look like this. In fact, in the future, most of us will be living in cities. 75% of the world's population by 2050. And the reason why iOS 1.0 will not work anymore is because the way we're running the world is killing our planet. And so we need to find smarter ways of providing buildings, because 40% of the energy we produce goes to buildings. We need to find better ways of transporting goods and people, because 25% of our energy goes to transportation. We need to find a cleaner and greener source of energy, because the fossil fuels that we use today are causing hundreds of billions of dollars of damage to people's health. And we also need to find ways to treat and distribute water in more effective ways. In California, where I live, 20% of all of the energy that we produce goes to moving water. We live in a dry state. But that will be the future in many more parts of the world as well. So we need an iOS 2.0, a new system based on small-scale generation, assets that are digitally connected, digitally controlled, and increasingly intelligent. And so I'm going to use the example of electrification because, as you saw in the previous slide, almost everything we talk about, whether it's transportation, whether it's water, whether it's food, is all driven by energy. And in the future, most of that energy will take the form of electricity. And let's consider transportation. If we electrify all forms of transportation, we'll need 75% more electricity by 2050. We'll start with things like buses and trains, already mostly electric, at least for new buses and trains. We'll also do passenger cars. Today in California, about 5.5% of new passenger cars are electric. So that's good, but we still have a ways to go. That funny thing you see on the water is something called a sea bubble taxi. It's in Geneva, Switzerland. It's electric. And we'll also eventually get to trucks and planes. A bit more difficult to do because the battery densities don't currently support long-range travel very well, but there's a lot of progress being made. So imagine that we're going to shift away from burning fossil fuels for transportation, and we're going to load that up onto the electricity grid. What would that look like? Well, it looks a bit like this. Because while we're adding more loads onto the grid, the source of that power on the grid is shifting as well. So today in the United States, about 17% of our energy comes from renewable sources. California is a bit higher. It's about 30% and going up. And this chart that you see on your left-hand side is known as the California Peking duck. You won't find it in any restaurant. What it starts to show is the shift of the net demand of electricity during the working day. And as recently as 8 or 9 years ago, peak energy demand was in the middle of the day. It was hot, air conditioners kick in, and that's when you had the most demand for power. As a result of the investment in solar panels, however, in California, that natural sort of peak in the middle of the day is turning into a trough. If we now add electric cars that are going to come onto this grid, which will mostly start to get plugged in at night when people return home, we're going to start seeing a huge shift of energy demand into the night, early hours of the evening. And this volatility in the supply of energy and the demand of energy is volatility squared, because we're putting more loads onto the grid, and the source of that power, solar, wind, is also inherently volatile. So how do we manage that in iOS 2.0? Well, the enemy is volatility. And as consumers, if you leave the lights on or you consume a lot of electricity today, you'll pay a premium for that extra spike in consumption. What you may not realize, though, is that if you're a commercial customer, meaning if you're this hotel, or you're a factory or a plant, demand charges, that spike that you see on this graph, will determine the rate that you pay for the entire month, and in some countries, for the entire year. So there's an extremely strong incentive sent via a pricing signal to a commercial user of electricity to shave those peaks. But how do you do that? Well, in the future, the energy grid will no longer be the thing that sits behind the meter. It'll be inside of your buildings. And this grid, or a microgrid, is going to have loads, meaning the lighting systems, the elevators, all of the things that consume electricity. It would also have sources of generation. It might have solar panels on the roof. It might even have a small wind turbine. And increasingly, there will be energy storage in terms of batteries. A lot of those batteries will be second life batteries coming from electric cars that still can serve a purpose once they're no longer as efficient inside of your vehicle. And all of these systems, in order to work, to shave these peaks, to know when to store energy, when to yield energy back, when to sell energy onto the grid, when to buy it from the grid, all of those systems inside of buildings have to become intelligent. And instead of one massive renewable grid, we will have millions of microgrids, all communicating, all coordinating. The challenge, of course, is the expertise. And I drew this graph after a conversation with one of our customers who pointed out that the moment of peak know-how that customer had was the day that we shipped them some new smart machine. That was like 100% know-how. We've been trained, we read the manual, we know how to use this. Great. And then it's downhill from there. Why? People leave, they retire, you forget, and so there's a natural erosion of skill and know-how. And in a world where a lot of the infrastructure will increasingly be built up of smart machines, we need to find ways of supplementing that erosion of knowledge, especially because a lot of this infrastructure lasts for decades. The people who buy it will leave it to their successors and sometimes to their successors. So the only way we can bridge that knowledge gap in smart infrastructure is to invest in standardization, open standards, making things more modular so that they're easier to put together, you don't have to figure out as much. And two that I'm going to be focusing on for the remainder of this talk, teleoperation and autonomy. So let's think about autonomy for a moment. What is autonomy? We tend to think of autonomy or autonomous cars, which is maybe the example that most of you immediately go to, as kind of like a binary condition. It's like it's not autonomous and it's autonomous. But it's really not. In fact, it's a continuing evolution towards increasing levels of autonomous operation. And at the base level, the humans are in charge. The next, the human's still in charge, but there's some assistance. Think like cruise control in your car. Think about maybe a rudimentary automation system inside of a factory. In the third level, the machine leads and the human supports. In the fourth, the machine leads and the human sort of checks in from time to time. We call this transition from human in the loop to human on the loop. And of course, at level 5, there may almost never be a reason to phone home and to ask for help. And we believe this level of autonomy will pervade all of this smart infrastructure in iOS 2.0. So it's not only the buildings, it'll be the factories, it'll be the grid, it'll be ships, it'll be buses, it'll be trains. All of that infrastructure is increasingly going to be intelligent. And let me give you an example, because so far I haven't actually backed up with proof points what I say. This is an example of a circuit breaker that we make, and this is part of what we call our ABB Ability portfolio. These are smart and connected pieces of infrastructure. And this circuit breaker is like your smartphone. It runs apps. So while it's sitting there in the basement protecting the circuits, it can do more. What can it do? It can measure the quality of power coming into the building. It can measure the loads on that building coming from all the different floors or the different parts of the factory of that building. It can also manage the energy generation, the energy storage, the heating system, the cooling system. So some basic building management know-how can also be provided as an app. And then we can extend this with third-party applications, such as predicting the weather, and in one in particular, which we recently announced, leveraging AI to predict these future peaks in power consumption, so you can hopefully shave those peaks and avoid those demand charges. So now let me talk why this is going to trigger an investment in AI, and specifically towards the cloud. And for the last 15 years or so, I've been in various roles where I've been saying computing is moving to the edge, it's all about the fog, edge computing, and I worked on a number of products that enable that. Well, I think the answer is a bit more nuanced. I think it's not just edge or just cloud, but there's definitely going to be a huge focus on the cloud in the industrial world, which up until this point hasn't really embraced the cloud. And it's going to go like this. The AI applications we need to make this infrastructure smarter, how do they get trained? How do we train a ship to navigate increasingly by itself? How do we teach a building to operate within safe conditions? How do we train a forklift to be able to move around inside of a factory without hurting people? We need to create not only the AI, but we need to infuse it with domain expertise. We have to tell it about the world. We have to tell it about the laws of physics. And then we need a digital twin, because in order to make this AI learn, we have two choices. We can take an autonomous vessel and then have it sort of randomly crash into sailboats and harbors and things like this until it stops doing that. Or we can create a virtual world in which it can happily learn quickly, and then once it's proven itself there, we can then unleash it into the real world. And therefore, I think we're going to see sort of a natural evolution. We're going to start with, let's first connect these intelligent infrastructure pieces. Then we'll have some kind of system to monitor it and make sure that it's not about to fail. Better yet is when we can predict that it's going to fail, and this is where the injection or the infusion of AI will start. And then we're going to find a way to overall increase the performance of these assets. One thing that many of you may not realize is that a lot of this iOS 1.0 infrastructure is dramatically inefficient. Half of the food we grow is thrown away or rots before it is consumed. We have manufacturing plants, among the best of them, that are only at 45% of their total theoretical output. The electricity grids typically operate at about 40% capacity. So if we get serious about optimizing the performance of this industrial infrastructure, we can do much, much better. And lastly, we can unleash all kinds of new and innovative models where we could potentially sell these infrastructure in new and innovative ways. So how do we get to the cloud? The promise of AI is that it's going to allow us to have all this smart infrastructure largely manage itself. But today, that is not the reality of how the industrial world works. The reality is today that almost everything you can think of from a digital perspective is on premises. It's in the factory, and it's not in the cloud. And when you look at it, what you discover is there's two kinds of applications. One we call the control loop. And the control loop, typically today, this is using devices such as programmable logic controllers, SCADA systems, distributed control systems. These are sort of like the the digital nervous system of a factory or a plant or a refinery today. And they sense, they analyze, and they act. And those are mission-critical loops. If something goes wrong, the factory breaks down, the chemical plant blows up, people get hurt. But there's another loop. And this is the asset loop, where you sense, you analyze, and you act, but you're not controlling the microsecond level response time of something. You're maybe just boosting the energy efficiency of this asset. You're increasing the yield by synchronizing the inputs and the outputs a bit better. So the cycle times tend to be minutes, hours, days, or weeks. So we'll start with all on-premises. This is the world of today. This is what industrial IT systems look like. The next step is when we recognize that we can make these systems smarter by adding AI to do this predictive maintenance, to do that condition monitoring. But where do we train the AI? And we have an example of this. We've recently created an application where we can sort through some trash. We can recognize different types of trash with a robot arm and then pick it up and move it into the right bin. To train this AI, you need oodles of compute. You need large data sets. Where do you do that best? In the cloud. But what you may not want to do is to close that loop between analysis and action and cause that action to be triggered from the cloud. Today, I would say most of the customers we have, they say, look, cloud for analytics, yes. Cloud for control, I'm not quite there yet. But I believe that that's simply the next logical step, to close that loop, to let an AI system in the cloud actually make a decision and send the instructions to cause something to happen. So now you close that asset loop. But we actually have customers that are starting to go all in. And they're saying, no, no, no. In the future, the sensing and the acting, that's sort of like my eyes and ears and my arms and legs, but I'm going to put my brain in the cloud. Why? Because I can get faster innovation, better integration. All of the benefits we have on the IT side for the cloud also apply for the OT or operational technology side. And therefore, I think it's inevitable as customers look to manage more of their systems through increasing levels of autonomy, they're going to naturally embrace AI, and on that journey to AI, it will naturally lead them to the cloud. So what do these eyes and ears and arms and legs look like? Well, they don't look like Arnold Schwarzenegger, but they might look like this. One example is our data center sheriff. This is a robot that goes into very large data centers and can swap out servers and disk drives and power supplies and things like this. And that can be scheduled. It can be given a set of tasks to do. And why not? Those data centers are getting very, very large. But we also have something more mundane called a motor crawler. So the casing of an electric motor, it looks like a metal drum. Inside are the coils and the windings. And between that casing and the windings is a bit of space. So we've made a robot that's kind of flat like a pancake, which you can insert in this inner space. And it can then go around and visually inspect the inside of the motor to make sure that it's still good to go for another couple of decades. And then in our transformers, so these electrical transformers, most of you recognize transformers as these drum-like things that are on a pole in the United States. Well, big transformers are more like these rectangular cubes. And the coils and the windings are in a bath of mineral oil. And if you want to do an inspection, you have to basically empty out all this oil, look at the windings, and then put it all back. The transformer diver is essentially a small, completely sealed robot that we can plunk inside of this mineral oil, and it floats around and it navigates inside, sending back images over Wi-Fi. And then the plant helicopter is a drone equipped with various sensors to detect methane emissions and other noxious gases, which can also help tremendously in terms of automating and controlling things. So these are the kinds of ways in which an AI or a brain in the cloud will sense, analyze, and act on the real physical world tomorrow. And increasingly, these will be more and more autonomous. In the beginning, they're probably level 1 autonomy with a human being doing most of the control and validation. But the next step beyond that will be that these systems become more and more self-sufficient. And while most of you know about Moore's law for semiconductors or Metcalfe's law for networking, I'd like to suggest that we need a law for AI. And the way to gauge the intelligence of an AI system will be to measure how many people we have versus these semi-autonomous systems. So today, for example, the kind of robots that move around inside of supermarkets taking inventory, the rough rule is 10 to 1. You got 10 of those, you need one operator, just to make sure that it doesn't get stuck or backs into a cardboard box and can't move anymore. But as these systems get smarter, we'll go to 100 to 1. We'll go to 1,000 to 1, because more and more these systems will be able to handle a lot of these corner cases, be able to make decisions, and not only to act and react, but to plan and learn. So I believe that increasingly we're going to measure the system's intelligence based on what I call an autonomy quotient, the ratio of people to semi-autonomous things. So if that's the case, do we still need people? And we believe that actually, as good as AI is, and we do need it, because all of this iOS 2.0 is going to rely on lots and lots of smart infrastructure that for most of its life, for most of what it does, will manage itself. But as we also see almost every day, AI today is limited. It's brittle. If the thing you wanted to show it wasn't covered in the training set, you don't quite know how it will behave. And if you're analyzing something like cat videos, it's not a big deal. But if you're running critical infrastructure where people's lives and their health depend on it, it is a big deal. And that's why we think that we're going to see for quite some time to come a combination. People are really good at being flexible, being creative, adapting to unknown circumstances. The AI is very good at applying a rigorous formula to data that it's been trained on, and it never tires, it doesn't have to sleep. And therefore, the best combination is when you put the two together. We call that a humane. And this humane has been proven to outperform AI alone or humans alone. In the cases of, for example, analyzing X-rays and looking for cancers, or recognizing images in criminology cases, for example. So we think that in control systems or operating complex machinery, the best combination will be essentially a symbiosis between AI and people. Thank you very much.
Well, you've definitely got me thinking, Guido, so thank you very much for that. Our next speaker is Brighton Shang. He is founder and CEO of Aquabyte. Please join me in welcoming Brighton Shang.
Thank you. All right, so how many of you had fish this week to eat? Chances are that fish was grown on a fish farm. My name is Brighton Shang. I'm the founder and CEO of Aquabyte. We're a company based in Silicon Valley and Norway that builds software for fish farms. Our goal is to make fish farming more sustainable using software and machine learning. Nowadays, most fish that we consume are produced at fish farms. This is a typical salmon farm in Norway. Each of the pens is producing anywhere from 100,000 to 200,000 salmon per pen. Over the course of a year, this farm will produce about 1 million salmon. It's farms like this that are producing most of the fish that we eat. We've been overfishing our oceans. The World Economic Forum estimates that we've depleted about 90% of our wild fish stocks. Because of this, most of the fish that we have consumed are from fish farms. In no other industry do we hunt and gather to get the food that we eat. In fish farming, this can be the solution. If you look at global food production, it's been growing at about 1% to 2% year over year. Fish farming, on the other hand, has been growing about 6% year over year. It accounts for about $250 billion worth of food production today. If you think about the world being 70% covered by water, we only have about 5% of our food production from the oceans. 5%. This represents a tremendous opportunity for us to be able to increase the amount of food that we're producing from the oceans. As we run out of land to produce food, it just makes a lot of sense that we're going to produce more of it in the oceans. Due to depletion of fish stocks, as well as the increasing demand for fish, we're going to need to be able to produce 50% more seafood in the next decade to be able to do that. And software and machine learning can help us produce more fish. If you look at fish, it's a relatively healthy food source. It's a great source of omega-3 fatty acids. It's also rich in vitamins and nutrients. 3 billion people every day depend on fish as their primary food source. It's also in places like China and India where folks are demanding higher quality protein. Fish farming is producing a lot of the fish that's helping serve folks all over the globe. From a carbon emission standpoint and climate and global warming, fish farming can also have a big impact. If you look at carbon emissions, comparing beef to fish, beef produces almost 7 times the amount of carbon emissions as fish does. If we can figure out how to shift a lot of that production to fish, we can make a meaningful change in being able to reduce the amount of carbon emissions and improve climate change. Also, from a bioenergy standpoint, if you look at how many pounds of feed it takes to produce pounds of protein, beef is about 7 to 1 in terms of pounds of feed for pounds of protein produced. Fish, on the other hand, is about 1 to 1. 1 pound of feed for 1 pound of protein is just a lot more efficient. Now, Aquabyte's goal as a company is to be able to use software and machine learning to be able to make fish farming more sustainable. So let's put on our fish farming hat. Imagine you're a fish farmer. You have a massive pen in the ocean where you're growing some fish. So how it works, you put some little fish in, you feed it every day, and then after the course of 12 months, then you harvest the fish. So as a fish farmer, you might be thinking a couple things. One, how much do I feed my fish? How healthy are my fish? About 15% of fish die in the oceans when they're grown. When do I harvest my fish? How much fish do I have to sell? This is something that's challenging. If you stand at the side of a pen, these pens are the size like half a football field in diameter. You can maybe only see about 5% of what's happening under the surface. And ultimately, how can we make these fish farms more efficient? How can we figure out how to automate feeding to be able to make these fish farms more sustainable? These are exactly the type of problems that software and machine learning can help with. So a bit about the company. I started the company in 2017. Genesis actually grew up in Ithaca, New York, right by Cornell University. One of our family friends was a professor of aquaculture at Cornell. And then ended up going to Princeton to study operations research and financial engineering, basically machine learning. And then started a number of companies in the machine learning and computer vision space. Started off in algorithmic trading, and also was the CTO of a company that used deep learning for cancer detection. The idea for Aquabyte started when I wanted to bring the same computer vision and machine learning technology to fish farming. The idea was simple. You take a camera, you put it in the fish pen, you take images of the fish, and then be able to use machine learning algorithms to be able to identify certain things about the fish. The size of the fish, the health of the fish, how much to feed the fish. I started off by building a simple prototype. So if you can imagine me in my apartment in San Francisco, I have a bathtub, and I built a simple rig in the bathtub. I bought some robotic fish off of Amazon. I put them in the bathtub, and I started to size the robotic fish. And it worked. We were able to determine the size of the fish. Now it was time to take this technology to an actual fish farm. And this is what I realized. The actual fish farms don't look much like my bathtub. They're actually pretty rough conditions. For anyone who's worked in hardware, they know that you put stuff in salt water to destroy it. And even basic things that we take for granted, keeping the camera functional, making sure that things don't break, is very challenging in the ocean environment. Also, connectivity. These farms are offshore, they're in the ocean. Sometimes they have internet, sometimes they don't. We're also dealing with the challenge of dealing with live animals. Fish, they have a mind of their own. They respond to different environmental conditions, they have different behavior, and being able to understand all of this complexity and develop it into the product is a new challenge. The second thing I realized was also that 99% of fish farming is global. So again, just to ask, how many of you actually know fish farmers? Okay, well, I should talk to you after the show. Species like salmon, they're grown in places like Norway, Scotland, Canada, Chile. It's all over the world. In fact, Norway produces 50% of the global salmon that we consume. And after looking at the market, I decided that, well, this business needed to be a global one. And we started a second part of the business in Norway. Now, the other thing to imagine is being a fish farmer. Fish farmers, they're used to buying barges and cages and nets and physical equipment. The bigger, the better. Now imagine someone from Silicon Valley talking to a fish farmer and trying to sell software. It's a bit of a different type of conversation. Part of this was understanding how to bridge the culture between Silicon Valley innovation and Norwegian fish farming. That essentially involved a lot of travel back and forth and just a lot of frequent flyer miles. Now in 2018, we had our first fully working product. Again, to give you a sense of scale, you could take an entire 737 and submerge it in that pen. We developed a simple camera rig. It's one camera per pen that goes and takes pictures of the fish. We're then using computer vision algorithms to be able to detect the size of the fish, the health of the fish, and various aspects, and provide that to a fish farmer. We spend the rest of 2018 being able to adapt this to various conditions, different weather conditions, different times of the year, to make sure the product was robust. In 2019, it was time to take it from one farm to many farms. Now, the thing that you have to realize about fish farming is that every fish farm is essentially regulated everywhere by a version of the EPA, because it affects the environment, and a version of the FDA, because it affects the food that we eat. To have a successful product, we needed to figure out how to create alliances. Alliances between researchers and academia, between the actual fish farmers themselves, and government. In Norway, we were the first company to build electronic replacement for sea lice counting, where you could actually apply to the government and use our counter to count sea lice. I'll get into sea lice a bit further into the talk, and you'll have the chance to count them yourself. We also had the chance to have CTO of Amazon, Werner Vogels, come out and shoot an episode of Now Go Build with us. If you haven't seen it, you should definitely check it out on Prime Video. It's episode number 3. Now, a bit about what we're working on. So again, we have these cameras in the pen. They're taking images of the fish, and we want to understand certain things about the fish. Now, the first thing you realize from taking these images is that while you're dealing with a lot of complexity, even just a simple task, like if I asked you to count the number of fish in the image, it's pretty difficult. You have fish swimming every which way, different orientations. You have particles in the water. It's a bit of a challenging application, and being able to do this in real time and understand the health of every fish. Now let's take a look at a single fish. Here, we're applying a convolutional neural network that's being able to detect the different body parts on the fish. We're then taking those body parts and using it to determine the weight of the fish. So let me give you an analogy. Again, for humans, we're measuring the different body parts, and like us, fish have proportions. We're using those proportions to understand the weight and ultimately using that as better intelligence for a farmer. The way the technology works is simple. So the camera, it has two eyes. Like us, it can sense depth. It has an array of LEDs on the top and bottom that helps illuminate the underwater environment because it's a bit dark. You also notice that there's some sensors on the side. So we're measuring things like temperature, oxygen, depth. We're measuring other things that we can help inform our system and be able to understand how the fish are growing. We're taking those images and then we're running it through an image pipeline. So you can imagine we have an algorithm that identifies and crops the fish. We have another algorithm that filters the fish. Maybe a fish is blurry, maybe it's too dark. We have another algorithm that's able to detect the body parts. We have another algorithm that detects the weight. We have another algorithm that detects the health, and so on and so forth. We string this together into one big image pipeline that then is able to process all of the images in real time. That then provides information for a farmer, and we provide this as a subscription service. So let me talk a bit about sea lice. It's actually a parasite that costs about 25% of the cost of running a farm. There are these naturally occurring parasites. They're about a millimeter in size, very, very small parasites. And every week, for every pen, the farmers need to count this parasite. On this image, you can't even see it. It's just too small. Well, let's zoom in a bit. So you can sort of see it. Two yellow specks in the middle. And if we zoom in a bit closer, we finally see the two sea lice. Again, they're like millimeters in size. Now imagine a fish farmer, every week, every pen, you saw what a fish farm looks like. They have to go out, they have to net the fish, they have to anesthetize them, they have to count one by one the number of fish, the number of lice on the fish, and do this every week, week over week. It's a really, really challenging problem. Our job was to make this a lot simpler for the farmer. The concept was, again, similar. We take the images of the fish, we'd be able to create object detection algorithms that could detect and classify the sea lice. We then was able to provide this to a farmer. Let's look at some infestation patterns. Here, the green line represents manual counting of 10 fish every week. Here, with our system, the red line, we're counting 10 times that every day. The farmer has better insight into infestation patterns and treatments which overall benefit the welfare of the fish. These treatments are also very costly. I mentioned it's 25% of the cost of running a farm, and having this intelligence is really important for a farmer. We wanted this to be a generalizable software platform, and we wanted to work on a number of different applications from the camera. Another thing that a farmer needs to know about their fish is how much the fish weighs. This is because as the fish gets bigger, you feed it more, and also they want to know how much fish they have available to sell. This is a picture of them using a crane to be able to weigh the fish. Again, super tedious. Our goal was to make this a lot simpler. Conceptually, it was simpler. We take the images of the fish. We then ran them through a series of deep learning algorithms that was able to detect the different body points on the fish and to be able to create a 3D model that could determine the weight. We then displayed this in a distribution for the farmer such that they could use this to manage their farm. One of the problems of building machine learning algorithms is that you need to gather training data. Now, for the underwater environment, this is a bit tricky. Let's just take a simple example. We want to build an image detector for a fish. Here we had a team of annotators that was able to detect each fish in the image and train the CNN to be able to detect the fish. Now, how about the ground truth weight of the fish? That's a bit tricky. So imagine your fish swims by the camera, take a picture of that fish, and the fish swims up. How do you know what the weight of that fish was? To do this, we needed to be a bit more clever. We worked with research institutions to be able to tag the fish, and then such that we could correlate each image with the weight. From this, we were then able to train our machine learning algorithms. Here's an example of some of the behind-the-scenes work of some of our algorithms. On the top, we're using a deep learning-based depth mapping algorithm. So again, with the stereo camera, we're mapping out the distance of every point on the image. We're then overlaying that on a segmentation of the fish. That then creates a 3D model that tells you the weight of the fish. We then applied this to every fish that we saw in the image. This then gave us a distribution for the weight of the fish. The farmer was then able to use this to determine how much to sell. So on the other hand of things, you have the Whole Foods of the world that are buying salmon, and they want to know how much they can buy each week. This technology is giving them that ability. Now again, the idea being that we want to build a common software platform on top of which we could build different applications. If you look at fish farming, about 50% of the costs is the food. They feed the fish these pellets. So if you've ever had an aquarium at home, how do you figure out how much to feed your fish? Well, you take out your food, you sprinkle a little bit in to see if the fish eat it. Maybe they do, maybe they don't. If they eat it, you sprinkle a little bit more. It's essentially the same thing that they do at industrial-sized fish farms, just at bigger scale. So we're taking an upward-facing camera. We're watching for downward-falling pellets. So the pellets that are falling down means that they're uneaten. And if they're uneaten, they just end up falling to the seabed and end up disintegrating. Here, we're building object detection algorithms that could detect every single pellet and be able to quantify the amount of feed wastage for a farmer. So here, we're detecting 99% of the uneaten pellets. This allows us to determine and quantify how much feed wastage there is and allow a farmer to better manage their farm. Now, I want to talk about some of the cooler technology that we've worked on. And yes, like you and me, fish have unique faces. Their spots are like fingerprints. Here, we built computer vision algorithms that can extract the spots on the fish and use it as a unique identifier for a fish. So a couple of you might be wondering, what if we saw the same fish twice? Well, we know that. We also know how individual fish grow over time. Now you can imagine going to a nice restaurant, you order your plate of salmon, you take out your phone, and like a QR code, you found out exactly how that salmon got there. Now combine that with the blockchain, and you literally have full traceability of your fish, literally from farm to table. Now, the holy grail of fish farming is a fully autonomous farm. The idea being here is that we can use a lot of the information that we generate from the images to be able to adjust how much feed is given. So the idea is simple. Let's just imagine that we're running lots of different A/B experiments. So let's just run an experiment where we have two identical pens, except in the second pen, we feed it a different type of feed, and that's 2 to 3% more efficient. And over here, we run another experiment where we have two identical pens, but one maybe we feed twice a day instead of once a day. We can then run lots of different A/B experiments to figure out what is the optimal policy for feeding our fish. Aquabyte's goal is to eventually build fully autonomous fish farms. In Las Vegas, if you eat a fish here, it needs to be trucked in from the Pacific Ocean or it needs to be flown in. Imagine having an indoor fish farm miles outside of the Strip where it's fresh fish, it's more environmentally sustainable, and it's more economic. Right now, the main problem is that most of the fish farms need to be by places where people can actually go to the farm. With automation, we can start to have indoor fish farms, and we can also have farms in the open ocean. Eventually, we'll be able to get here. Now, to be able to do this, we need to learn to process a lot of images. So to give you a typical sense, every one of our farms, we process about 1 million images a day in real time. Now for us as a startup, we've been around for 2 years, we have about 10 customers. For those 10 farms, if you do the math, we're processing about 10 million images a day, or about 1.5 petabytes of images every month. That's a tremendous amount of images. Now imagine going from 10 farms to 10,000 farms. To do this, we're going to need to build a lot of new knowledge, new alliances, and new infrastructure, and it's going to have all of you to help us to do that. We need to start on the cloud, and then we need to figure out how to scale to the edge in places where there's low connectivity and to make the processing more efficient. We need to figure out how to automate more of our algorithms and be able to do that such that we can process a lot more efficiently. By 2030, there's going to be 1 billion more people in the world. Aquabyte's goal is to be able to make fish farming more sustainable. Again, with the world being 90% covered by water, again, or 70% covered by water, we only have about 5% of our food production from the oceans. That's a tremendous opportunity for us to be able to increase the amount of protein that we're growing and in ways that are a lot more sustainable. It's going to require the help of all of you to be able to build technologies that can be able to process images more efficiently. I hope you can all join me in being able to make fish farming more sustainable, and together we can figure out how to sustainably harvest the oceans for generations to come. Thank you.
Thank you very much. Wow. I just learned more about fish farming than I ever thought I would know, and what a great use of machine learning and AI. So we are now at our break, and we'll return at 3:45. So don't go away, don't go too far. Please come back, and you'll have 4 more excellent speakers. Thank you so much. For those of you who are just joining us, welcome to the AI and Machine Learning Summit. Again, I am Michelle Lee, Vice President of the Machine Learning Solutions Lab. Earlier today, we had 4 excellent speakers on a range of applications discussing of applying ML. They discussed cancer research and T cells. They discussed social media feeds and how they can be used to quickly identify natural disasters and the status of them. We also learned about and got a glimpse into our society and what the infrastructure might look like on a going forward basis. And then finally, we heard most recently about the use of AI and machine learning for, of all things, fish farming and how it might be done more sustainably for the future. So up ahead, we have 4 more outstanding speakers on a wide range of topics. And next up is Dilip Rao. He is the Vice President of Research at the AI Foundation. So please join me in welcoming Dilip. Dilip?
Hi, thank you.
There you go.
Hi, everyone, and thanks for coming. My name is Dilip, and I work at the AI Foundation. At the AI Foundation, we work on a variety of generation and detection problems using deep learning and a lot of other technologies related to it. And particularly the problems that I'll be talking about is actually on deepfakes. The problem that Michelle was mentioning, like about disasters in social media, reminded me of another kind of disaster that is actually happening in social media today, which is that of misinformation. So today we are going to look at some solutions that AI Foundation and our partners are working on this misinformation problem. So it's not a surprise to anyone today that any video content that you see can be questioned, and the word deepfake itself has become a household term, right? And so we all know that seeing is not believing, and the same thing applies to hearing as well. So, and if you look at some of these examples, these examples you might have seen on the internet, for example, and some of them are very cute and funny. They appear even in comedy shows, and many of them are like downright scary, right? And the same thing applies for audio as well. Like, it's not just visual fakes. Speech today can be cloned to the likeness of your voice in a way that was not possible before. And this has been used, the technology behind this, like voice synthesis, or speech synthesis and voice conversion, they have existed for years. And it's only today that we have these new technologies that allow us to produce voice in the likeness of anybody's voice signature. And this has been used successfully by people to rob banks, to mislead executives into signing fraudulent wire transfers. So this is kind of brewing an information credibility crisis, if you will. And there are, I would say there are two sides to this credibility crisis. One is our inability to trust the real world. That is, basically, it is coming from this ability to show anything fake and call it as real. And the other is the opportunity for plausible deniability, where we can we can basically refute anything. So it's basically our inability to show something real as real. So, and you can always say, oh, this is fake, right? And how do we counter that? So this is actually a real problem. And fake media is not new. So the image on the left is something that you might have seen in a lot of classrooms, right? So this is Lincoln standing. And this is not Lincoln, actually. It is actually, when they were trying to find a standing portrait of the president, they couldn't find any. So they took John Callahan standing portrait, and they just put his face on it. And this has been the standing portrait of Lincoln that we use everywhere, right? And this is not any secret. Everybody knows this. And then Photoshop has happened, and we've come a long way from this. But then, in the last few years, things have gone into a sort of Cambrian explosion, if you will. In 2014, we are able to generate images that were black and white with very low resolution, and it was very hard to make the details of the face clear. And as we progress over the years, it is becoming we're pretty much crossing this uncanny valley. And today we are getting to a place where we can generate images of or generate faces with very high amount of detail. So And there is also another interesting exponential growth happening, and that is of social media. So as social media adoption is increasing, so is our capability to share it with share or distribute messages exponentially is also increasing. So virality is becoming a new phenomena. If you just think about it, going viral did not exist before social media, unless it was printed in mass media before. And so this is coupled with a lack of education and media consumption. We never went to classes where we learned how to consume media on the internet. So all these three things, the exponential growth in generation technology, the exponential distribution capability that comes with social media, and the lack of education in how to consume this kind of information is fueling this perfect condition where what I call as the misinformation singularity, where you get into a place where you don't believe anything you see and hear, unless we do something about it. So the question is, what are we doing about it? There are a lot of people who are working on this problem. I'm not saying only AI Foundation is doing this, but I'm going to focus on some of our solutions. We're starting with the 2020 election. We're building this platform called the Reality Defender. And the goal of Reality Defender is to become a formidable tool in this fight against deepfakes. And not just the video deepfakes, but also audio fakes and so on. To unpack that a little more, the goals for Reality Defender is, one, to bring the latest and the greatest from AI research and forensics research to production. A lot of the work today exists in laboratory conditions, in the sense that you cannot take the code that you have from a researcher and then deploy it in a product setting, because in the real world, the distribution of the input data keeps changing, and many of the modeling, et cetera, and the state of the art that we see are built under IID assumptions, right? And then what is really needed and what we are working on is to create this interdisciplinary collaboration between academia, technology, startups, and the entire technology ecosystem, including large cloud companies, as well as the government, because we need the government actually acting and working with these companies and with academia, and also the media and entertainment industry. These are just a few of the many stakeholders who are impacted by this deepfake and misinformation problem. And the other goal we have is to build accessible tools, build tools that not just somebody who has a PhD can use this, but also some tools that could be used by journalists, fact checkers, and anybody who's actually interested on a self-serve basis. And so you can see how scaling something like this from something that I did in my lab to something production worthy that everybody can use requires a lot of participation from people, as well as a lot of compute. And finally, another goal of Reality Defender is to push the boundaries of science around misinformation research. And we're doing that by establishing not just these collaboration with academia, et cetera, but also creating data sets, resources, and models and open source code and so on to advance science and to have and sponsor conferences and things like that. So I'll walk through some examples of the work we have done under Reality Defender. In 2017, we funded the Technical University of Munich for the creation of the face forensics dataset, which is the first deepfake dataset that was ever created. And the goal here was to build a large enough data set so that modern machine learning methods could be utilized to build models for countering deepfakes. And of course, many of these deepfakes produce artifacts that are very similar to the compression artifacts. So it is important to generate this data or create this data set at different compression levels. And this is the first time something like that was done. And as a result of this, we produced a lot of models that can do deepfake detection, but still under laboratory conditions, right? It's not in production. For instance, we could learn a model that can detect a deepfake very well as long as we know the method where that was used to produce the fake. But if you have a new method or a lot of examples from a new method, it becomes, if you don't have a lot of examples from a new method, then it becomes really difficult for the model to produce good results. And not just detection, we are also interested in identifying the exact area of the image or the video that is manipulated. And this sort of model, being able to explain the prediction of the model is crucial in earning trust of the users, because you can't say, oh, this piece of content is fake and just leave it there, because people will not trust your system, right? And segmenting and identifying. So here you can clearly see we are using some kind of a computer vision segmentation algorithm, and with the segmentation algorithm is specifically focusing on areas that are manipulated. So then this is another area of work where we looked at this problem of changing adversaries. So we have all these different methods for generation of fake content. And then when we train a model for detecting a deepfake and try to use that model on this new adversary, the model fails. So the question is, how can we quickly bootstrap models for these changing adversaries, right? And here we use transfer learning, and our approach is called forensic transfer. And in the paper we show a very simple example where, let's say you're from the Department of Interior, and you wanted to know if certain images of forests and all these other national parks, etc., have been faked, manipulated in some way to mislead people, right? And you have, so this is a brand new misinformation problem. But let's say we have a model of fake faces that can, model that can detect fake faces. Then the question now is, can we use this model to quickly adapt or quickly fine-tune a new model that can detect manipulated, geographical areas. So that's called forensic transfer, and we've been successful in doing that. And we just take a few images, in fact, less than a dozen images, to quickly train and increase the accuracy of the model, right? And obviously, this works not across domains, but also even within domains. So let's say if there is a new fake generation method comes along, then we can apply this as well. And so these were some examples that I showed that were purely using pixel level information for detection of fakes. But then there are a lot of other interesting information that is present in a video that could be used, for example, like context. So I'll give some examples of algorithms we developed with Professor Hani Farid at UC Berkeley. And so here we look at two different signals. One is the orientation of a person's head and what the person is speaking. And we kind of extract a behavioral signature of a person's head movement when they're speaking. And this actually is true because when we speak, we tend to have similar head movements for the certain kinds of sounds we produce. And if there's a mismatch in the head movement versus the actual sound that is being produced, then we can detect that, and that can be used for discriminating fakes in a very pixel-independent way. It's remarkable. And obviously, we can do that even with facial expressions. So in this case, we use the FACS encoding, which is facial action coding system. And we can extract expressions, and then can expressions be used to create a signature for a person? And can that be used to distinguish whether a particular piece of media was tampered? And this is interesting because we have, especially in the context of the elections, there are several people of interest, right? The presidential candidates, for example. And you want to be able to identify any tampering for these special candidates. So these are people of interest models, as opposed to the general purpose models that we talked about earlier. And these models tend to be a lot more accurate. And finally, there are all these, so all the examples we saw so far were for for video and image detection. We can also apply the same methods or variants of the same methods for detecting audio fakes. So in this work, what we are doing is using a convolutional network and using both multitask learning as well as transfer learning to quickly train models for different kinds of audio spoofing methods. And we are able to detect manipulations in audio with very high accuracy and with very little amount of data. So for example, going from, let's say, one attack vector to another, we can now cut down the amount of data to around 6%, which is a couple minutes worth of data, right? And that's incredible. And we are also releasing a brand new data set around detection of audio fakes. And this data set will have around 500,000 examples from a large number of speakers, as well as one thing that we wanted to make sure was the data set was very diverse demographically, so that way the models don't end up becoming biased towards a specific category. So far, I talked about various machine learning approaches for dealing with misinformation. But machine learning approaches are just one, and in fact, all kind of software-based approaches are just one kind of arsenal in the artillery, if you will. There are other two parts of this puzzle, or the solution puzzle, that is education and policy. I'll briefly touch upon that, and we're actually talking to policymakers as well as people who are in the education space. But I think it's important for all of us machine learning and data science practitioners to actually become aware of some of these efforts and actually see how they interact with the kind of technology solutions that we are building. So I'll first start with education. So as I mentioned earlier, we at least when I grew up, I never took any course on how should I be reading Reddit, for example. But on the other hand, today we can create new content, new courses specifically tailored at high school students, university graduates, undergrads, and to actually ask them how can we examine a piece of content in the context it was created, right, or in the context it was shared, and what is the credibility of the source where they got the content from. How was the content constructed? Was there any bias or what are some loaded words, biased terms that people use in describing content, describing any content that can make it very one-sided, if you will? And then how to corroborate whatever you see with other sources. So what do other news sites say about this, and so on? And what are the tools for doing that? And then how to compare, right? And also compare with your friends and colleagues, right? And there is, I want to give one very shining example of this, which is, it's not a PC name. It's called Calling Bullshit. And it's a very beautiful course. It's available for free for everyone to take. And it's created by Jevin West, who is a professor at University of Washington. And now this course is being taught in a lot of different high schools and even in university level. And the goal here is to see, okay, can we spot misinformation when we're consuming news articles, scientific literature, or any kind of social media post. So then there is this other big part of the puzzle that is policy. So there are so many things here that I'll never have time to discuss, but there are a lot of questions than answers, unfortunately, or fortunately, depending on your view. So how should information safety be enforced, right? Can we just let people just consume whatever they want, right? So the other side of the question is, should it even be enforced, right? So, and then should there be some sort of overseeing body at the federal level that should do this? Or how should this happen? How should this governance happen, right? And then what are the laws around this, right? So if somebody creates some misinformation, what are the consequences for that, right? So what is the legal and policy scholarship? And people are working on it. And there is a law that got passed in California, for example, where, basically it's almost a ban on deepfakes without creating any kind of context. And a similar deepfake ban was enacted just a couple days ago in China. And this is interesting because on the one hand, we really need this kind of legal frameworks for understanding these different kinds of media misinformation attacks and misinformation, or dealing with these misinformation attacks and forgeries. But at the same time, there is always this danger of overreacting and overreaching, especially legally, because and act laws in a way that can stifle innovation, right? And this overreaction can come simply because we don't yet understand what is in front of us. And that's dangerous because once something gets enacted as a law, it takes several years for the law to change, whereas innovation requires rapid changes, right? So we have to, on the one hand, we need to have these legal things in place, but on the other hand, if we don't, as technology industry, if we do not participate at the level of policy and governance, then we will risk getting our innovation capability clipped in some way. So I want to say that deepfakes are here to stay because starting from these toy project, projects that you have seen, like coloring the horse into a zebra, etc., or turning the day into night, and so on, to the kinds of products that AI Foundation and other companies are building. The thing on the right is an example of a deep fake that was generated completely from scratch, and it can talk and do anything you want to make it to do, right? And this is, as you can imagine, these sort of technologies have a lot of impact on education, on entertainment, and they can open up new applications in ways that we cannot even imagine today. It's kind of like internet. internet opened up whole different kinds of applications that people who created the internet did not even imagine. So we cannot afford to curtail innovation in this space, but at the same time, we cannot also be complacent. We have to act responsibly, and we also have to act with care. So I'm going to leave you all with this message, but I really hope that this talk is not the end of this conversation, and I hope you'll all join me in this conversation later as well. And I also want all of you to come and work on these problems, because the scale of problems that we are looking at is not like a single startup or even a single big corporation level problem, but these are gargantuan internet scale problems. So with that in conclusion, I really thank you all for coming and for listening, and it's been a pleasure. Thanks.
All right. Well, there's a lot to think about there, and a lot for us to do collectively with all of our wisdom to hopefully move forward some of those issues. So our next speaker is Henry Stuhl. He is with Bowery Farming, and he is the Senior Vice President of Science and Technology. Please join me in welcoming Henry.
Thank you, Michelle. Again, my name is Henry Stuhl, and I'm the EVP of Science and Technology at Bowery Farming. And today I'll be talking about how we use AI to optimize our indoor farms of the future. Before we dive too deep, I want to give you guys a little background about Bowery, who we are, and some of the problems that we're solving. Bowery is the modern farming company growing food for a better future by revolutionizing agriculture. Now let's talk about what that means by looking ahead into the not too distant future in the world we'll all be living in. The year is 2050. The population will be growing to exceed 10 billion people. Now imagine that population being ever focused in urban areas. Now imagine the stress that population will put on our global food supply. We need to modernize farming because it's a market that has to grow. Some more facts. Over 70% of our annual fresh water supply currently goes to farming practices. Over 1 billion pounds of pesticides are used in the United States alone. And 30% of the arable land in the United States is already used. Traditional farming just won't meet this demand. We won't meet this demand because the supply chain is also complex and fragmented. From farm to processing to shelf. The opportunities to increase shelf life and nutrition while decreasing waste, cost, and time are enormous. These challenges and opportunities exist as we progressed through the 21st century. At Bowery, we're building part of the solution to this problem. We're building a network of warehouse-scale indoor farms where we can grow produce 365 days a year, indoors, hydroponically, without soil, using LED lights. And we do that while using 0 pesticides. Our vertical farms are over 100 times more productive with land use than a traditional farm. And because of our closed-loop, recirculating hydroponic systems, we're over 95% more efficient with our water usage than a traditional farm. This is the future that we're building at Bowery. And behind me is a glimpse into one of our larger farms. Now, there are several key factors that enable us to build that future today. The first is one that many of you have heard about. It's LED technology. The trend in both a decrease in cost and an increase in efficiency over the last decades is certainly a key to enable this technology today. But there's more. In order to build a truly scalable system, we believe that indoor farming must sit at the nexus of several key technological trends. Advances in custom sensor technology, robotics and automation, computer vision, and artificial intelligence are all keys, all parts of the puzzle to get us there now. Now, before we dive into what contributes to these advances and how they work in our indoor farms, we already looked ahead a little bit. Let's take a moment to look backwards at the evolution of technology in farming. Imagine a farmer. Let's call him Farmer Tom. 10,000 years ago, Tom planted some seeds. He fed them, let the sun shine on them, eventually harvested them, and fed them to himself, his family, and maybe his village. Wash, rinse, and repeat, over and over. He ended up picking what seemed to be, to him, the best seeds to grow, to solve his problems. For most of time, this cycle repeated, developing some new technology along the way. Fast forward to the 1900s, that technology that was available to Tom becomes more mechanical in nature. Eventually, Tom needing to feed whole cities, that technology had to evolve to include the use of chemicals, pesticides, fertilizers. This allowed him to grow bigger crops on smaller amounts of land. Today, Farmer Tom has used up much of that land that's available to him. And he's actually started to destroy a significant portion of that because of those farming practices. And he still needs to feed this population that's growing rapidly. We bring Farmer Tom indoors into the farms of the future. Tom now has full knowledge of every single variable that goes into growing the best quality crops. Now, at the core of our farms is technology to monitor, control, and operate these complex systems, our farms. That tech is what we call the Bowery operating system. The Bowery OS is software, hardware, and AI tools that allow us to operate and learn from our farms. Operating can mean things like, how do we turn the lights, the fans on and off? How can we change their intensity? How do we turn irrigation on and off and control the flow of water? It also happens to mean, how do our farmers on a daily basis know what they have to do, when they have to do it, and where it needs to be? Now, when we talk about learning from our farms, we're talking about how do we improve both yield and quality over time. And I like to think about this type of learning as a sort of flywheel. We grow in our production facilities, we collect vast amounts of data, we learn from that data, and we feed those learnings back into our production farms. Wash, rinse, and repeat. That is our cycle. And of course, there's also more that goes into learning from our farms. There's also the learning of how do we be more productive and utilize the space and resources available to us. Now, traditionally, farming technologies, particularly indoors, have been formed by a hodgepodge of disconnected systems. There's irrigation, which is the movement of water, fertigation, which is the mixing of nutrients into that water, the systems that control them. There's lighting control systems and automation control systems. And of course, there's our plants. The Bowery OS connects first and third-party systems that magnify the capabilities and knowledge of the farm as a whole. So what's an operating system really? A simple way to look at it is it's software that connects hardware to other software and applications, usually with a communications protocol. That's exactly what the Bowery OS does. We have custom-built hardware, software, and integrations with third-party systems that can now all talk to one another. We remove this disconnected hodgepodge and bring it all together. And we control and sense and monitor almost everything that goes into growing our crops. Things like temperature, humidity, CO2, those are easy to understand. How the air flows over our crops, what nutrients we're feeding to our crops, where the crops live, what type of water they're getting, how close are the plants together. We've made it possible to now track the inputs and outputs of everything we grow. Now, that ability is the first part of an unlock for us to learn more faster than ever before. And again, learning, in this case, we're talking about how to improve the output of our farms in both yield and quality. The second unlock is how our farms operate. Our farms operate much like an assembly line, where every day we plant, harvest, pack, and ship. Every day. Now, if we think about each group of plants that we sow, that we plant, as a crop, as a singular unit, something really interesting happens. We go through over 100,000 crop cycles a year in one of our farms, much less a network of farms. Each of those crops I think of as a learning opportunity. The tricky part, you can't just learn, because at the end of the day, we have customers. We're feeding people. And so wherever we have to learn, we have to balance that with production operations. Now compare that to the rate of learning in a traditional farm. Most farms outdoors have somewhere between 1 to 6 crop cycles a year as learning opportunities. It's not much of a comparison, actually. The key to learning more faster is measuring and understanding the inputs and the outputs. Really, this is the setup for a great optimization problem and use of AI to increase both yield and quality over time. It's what we call science at scale at Bowery. This application of machine learning has parallels to what's known as the multi-armed bandit problem. This is perfect. We're in Las Vegas. Picture an octopus sitting out on a casino floor. The octopus sits in front of slot machines with its 8 arms and starts playing slots. It starts to pull with each of its arms. And for the sake of the example, let's say with arm 7, it starts to realize a higher rate of return on that slot machine. Well, the octopus should start to exploit that knowledge and start to pull that slot 80% of the time. At the same time, exploring with each of its other arms. Until the octopus finds, with arm number 2, it starts to see a higher rate of return. And so now the octopus switches its exploitation to arm number 2, and again starts exploring with its other arms. This problem was really interesting to me when I first learned of it. And I thought, what are our levers to pull? recipes. This is Tom Colicchio. He's a chef, he's a TV host, an advisor, and an investor in Bowery. He thinks about plating his culinary plates by forming combinations of ingredients into recipes, tasting, observing, but ultimately converging on perfection. We do the same thing with the produce that we grow. So, what goes in to the perfect recipe at Bowery? I've talked about many of these already in this list. Things like temperature, humidity, CO2. There's light intensity, right, which is how much light is shining down on our plants. But there's also photoperiod, right, which is what's the day-night cycle a plant sees. There's light spectrum. What color are the plants getting? What direction is the airflow moving on top of our plants? What type of nutrients go to different types of crops? Where do they live? How close together are our plants? What is the plant density? There's trillions of permutations per cultivar. A cultivar is a type of seed. Pulling one lever at a time, it just doesn't work. Making one manipulation at a time just doesn't work. It would take forever to get through all of the combinations. Also, with our type of control, we're talking about dynamic recipes. So we're not saying a crop should have a certain experience for its whole life. What we're really saying is we can break this down into smaller chunks. What is the crop experience week by week, day by day, minute by minute? The number of permutations explodes. Now, to really experiment, to drive yield and quality, we really have to know good from bad. We need to have to know what impact we're having by making tweaks here and there. We have to understand how we're changing the growth rates of our plants. Now, I mentioned this earlier. We've built custom hardware. We built a camera system that monitors the growth of all of the crops growing in our farms, every single one. The first application of AI I want to dive a little bit deeper into is how we use deep learning to make sense of all of our images from our camera systems. This is a video of one crop with two different views. What I realized is looking at videos of plants growing, I could actually watch these videos all day long. It's fascinating. You see, it looks like the plants are dancing. It's really spectacular. What we're seeing from this image, on the left, we're classifying what is plant versus not plant. And we're taking, from that classification, information to generate growth curves for points of comparison as we're pulling all of our levers. The red line on the bottom left shows one of those growth curves. Now on the right, I mentioned there's two sides to this coin. It's not all about yield. Yield always comes at a cost of quality. So on the right, you can see an example of another type of classification that we perform. In this case, we're detecting quality defects, purpling of arugula in the bounding boxes. And we can monitor how the changes of inputs affect our outputs. We can tell, are we doing good or are we doing bad? Which, remember, is critical. We're selling these crops. It can't just be about an experiment. Our farmer, Tom, can now participate in this exploration versus exploitation problem. He can implement and track many experiments at the same time. What you're seeing here are the outcomes of one example of this recipe search. It's a simple example. It's really more like an A/B test, where different data points, different colors represent yield outcomes for various recipes introduced. what you see is as we learn a recipe has a higher yielding outcome, we drop off the recipes that have lower yielding outcomes. I mentioned this is a simpler example. It's more of an A/B test. What we're doing in our farms is A, B, C, D, E, F, G. We're analyzing hundreds of recipes all at the same time. Now, science at scale of this form is enabled by knowledge of all the inputs via the Bowery operating system, custom hardware with cameras using deep learning to analyze those images, and measurement of all the inputs and outputs. We have the ability, for the first time, to create a machine for improvement. That improvement gets us converging to that perfect recipe. Now, there are, of course, other problems we've encountered as we've built and operated our farms. For instance, when you look into the window of one of our farms, from a certain perspective, mine as a physicist, I look up and I see a 3D matrix of available locations to put crops. Now, when I would come into our first farm, I would look in the window early in the morning, and I would ask myself two questions. The first, how do you decide the order to do your work at the beginning of every day? The second, how do you decide where to put things back at the end of the day? Those two questions used to take probably somewhere on the order of like an hour to two every single day. That was tough in our first farm. Since then, our farms have grown almost 100 times in size. And it's near impossible for a person to answer those questions, those seemingly simple questions. Really, this is just another optimization problem for us to solve, again, with clear constraints. It turns out butterhead lettuce likes to live near butterhead lettuce. If it can't, it'll take romaine. Romaine and butterhead can grow next to each other. It turns out both of those don't like to live next to kale or arugula. Every day in our farms, machine learning algorithms run and tell our modern farmers what crops to grab, in what order, and where to put them at the end of the day. They're seemingly simple questions that are really hard to solve. And the tough decision-making doesn't stop there. As we follow our crops through their life cycle, when they're harvested, we have more hard decisions to make. One thing I haven't talked about yet are the types of things we grow in our farms. Well, we grow butterhead lettuce, I mentioned, romaine, a few types of kale, arugula, mustard, bok choy, arugula, spinach, basil, cilantro, parsley. We've actually grown over 200 different types of crops in our indoor farms. The problem we have is when we harvest something like romaine, we have to make the choice of how we fulfill orders with that romaine. We sell romaine as romaine lettuce. We sell romaine mixed with red leaf lettuce as a spring blend. How we allocate our product into clamshells, cases, and orders fulfilled has to be done in a way to avoid loss and maximize order fulfillment. This is just another example of complex decision-making that we treat as an opportunity to use machine learning for to aid in solving. Really, remember, this is to really aid in helping fulfill our overall mission, to grow food for a better future, and to democratize access to the cleanest, freshest product possible. This was Farmer Tom then. He was using what tech he had available to him to feed his villages, later cities, eventually the whole country. But along the way, it came with a cost. Natural resources destroyed, and natural nutritional loss and waste along the way on this complex supply chain. Yes, we brought Farmer Tom indoors into our vertical farms, but there's so much more. There's the connection of first and third-party systems enabled by the Bowery operating system. There's the rate of learning that's now available by doing science at scale in our farms. Now, in our network of farms, all connected together, benefits and learnings from one permeate to all. Tom can now be scaled infinitely. This is actually Farmer Tom today. She's enabled to make tough decisions, leverage the intelligence of science at scale in a way that's really never before been possible. She can easily grow the cleanest, freshest, most nutritious product and deliver it to consumers within days, not weeks. From my perspective, that's truly remarkable. I really thank you for coming today and joining me as I shared how we use AI to optimize our indoor farms of the future. Please do visit our website to learn more about who we are and what we do. And of course, feel free to check out our open roles. We're hiring for machine learning, software engineering roles, and beyond. Thank you.
Thank you. Fascinating. Next up is Judith Dexamer. She is with the Cincinnati Children's Hospital Medical Center, where she is the Associate Professor, UC Department of Pediatrics. Please join me in welcoming Judith.
Thank you. Hi, so thank you everybody for coming and for staying out, because I am pretty sure the afternoon is beautiful and we aren't outside. But so I want to give kind of a brief introduction about myself before I get started. So I'm Judith Dexheimer. I do pediatric research, and so I'm very friendly because pediatricians are very friendly. But what I want to tell you is a little bit about myself. I'm not a pediatrician, but I work with them. Is that I am actually an introvert, but in the land of informatics, I appear to be an extrovert. And so I'm going to do my best today. So the first thing I want to do is audience participation, and I want to ask who used to be a kid? You can raise your hand. I'll raise my hand. And so who is still a kid? So excellent. So what I wanted to answer first and foremost is, why would we study pediatrics? And that easy answer is because everybody was a kid once, and everybody begins to grow up. And so what happens in pediatrics is sometimes little kids get sick. And part of what we want to do when a child gets sick is detect whatever their disease or illness is as early as possible, because an earlier detection could lead to an improved quality of life. And so another issue that appears in pediatrics all the time is medications. So for the first couple of slides, you're going to be patients, and you are going to have strep throat and go to your provider and say, you know what, I think I need something. I think I need an antibiotic. So we're going to do this with a pediatric patient as well. And so your child is going in and they're sick and they need something. But one of the problems with medications in pediatrics is that when they're tested in clinical trials, they're not tested on kids, but they're still prescribed to children. And so from the machine learning side, there's a wealth of information living in an electronic health record all about what a medication does and any possible adverse events that a child might have had taking it that could later be mined that aren't collected when they're talked about originally and tested. And then the most important thing that I want to stress during my 30 minutes today of talking to you is that healthy kids lead to healthy adults. So if we can make healthier kids, then we can make an overall healthier population. So I mentioned I was at a pediatric hospital. And so what I want to show you on this slide here is that we don't just have pediatric patients, we also have pediatric providers. The real answer is this is my son, Steven, learning to wash his hands at a science center. And so what is pediatrics? Just so that there's a broad definition so that everybody's on the same page. And it's basically the medical care of infants, children, and adolescents. And so 1/5 of the United States are pediatric patients, so they're under the age of 18. And so one of the challenges in pediatrics and with pediatric data is the age-based variability. So the example I have up here is if you, when you're presenting with strep throat and you have a fever of 100.8 degrees, what do you do about it? Do you take some Tylenol and maybe go back to bed? If it's your kid, what do you do? Do you take them in to see their doctor? Do you call their pediatrician? Do you call your own doctor? What if it's your child who's under 28 days of age, and so it's a neonatal child? That child needs to have a call to their pediatrician and likely needs to go to the emergency department. So this is one data point that has very different things that may happen depending on who you are and how old you are. And then the second, Then the second example I want to give you here goes back to those medications. So medication dosing in pediatrics is based on a patient's weight. So once you're, say, an adolescent, you're a teenager, you're an adult, and you go in and say, I have strep throat, and your provider agrees and says, you know what, we're going to give you an antibiotic. You get a couple of pills, and you go home with them, and you are in charge of taking them. On the pediatric side, when they go to write that prescription, they're going to take the child's weight, and they're going to look at your weight, and they're going to say, here's how much you should be taking and how often you should be taking it. So again, one action that's going to have various consequences depending solely on your age. So this is our hospital. This is our new T building. It's currently named the T building. If you know anyone who would like to provide some money to help give it a new name, please let us know. But this is part of the place where we do research in the hospital. And so what are some of these interaction layers that are different in pediatrics when it comes to doing care and recording the notes that we're going to talk about in just a minute? One of them is there are multiple historians for medical histories. So you as the patient get to say, this is what I'm feeling, this is what's happening, please record all of this in the chart so I know what's happening. But when you bring in a child, the caregivers may have something to say, be that mom or dad or somebody else. Family members may be there and may have something to say as well, and they may have an opinion to give on what's happening with the child. And then once your child's an adolescent or maybe 10 or 11 years old, they have their own opinions. The child in the last picture is 11, my son Steven. He has his own opinions now. He wants to participate in his care as well. And so this brings us to who performs the patient's treatments. Is it mom? Is it dad? Is it the kid themselves? Again, you, with your antibiotic, know that you need to take it 2 times a day or not. Or you need to tell your child that it's time to drink that little pink liquid and make sure that they stay compliant with their care. And then the last thing that I want to talk about on the pediatric side is that there's a dynamic patient history due to their developmental stages. So an adult has a fairly static trajectory. You can guess that I am going to be about the same in 2 years as I am going to be right now. But if I want to bring in a 3-year-old, they're going to be very different in 2 to 3 years, and they should have started school, and they should have a lot of growth, and there are some underlying genetic changes. And so all of these things need to be taken into account when starting to look at some of their medical data. So let's start with the electronic health record, again, so that everyone is on the same page. Probably you have had an interaction with the electronic health record in your life. What's in it? Everything about your hospital visit now. Your chief complaint, so why you came in for your visit that day, your temperature, because you had your temperature taken when you walked in the room, your weight, so that they can compare it to last year and say, how are you doing? But it also has all of your provider notes, all of their communications with you. It has all sorts of fabulous and rich information being used for clinical care, being used for billing, being used for communication among all of your care team. So what's important about electronic health records is there are more than 300 EHR vendors in the United States. 75% of hospitals report using an EHR or have one installed, and more than 80% of pediatricians report using one when they do care in patients. So there's a lot of data that's being created all the time. So what's in there on the terms of data types, just so we know what we're working with? The first is quantitative data. Those are the structured data. So when you go in and have your temperature taken and your respiratory rate, those are structured data. Those are stored in the EHR. When you have a diagnosis, when you leave your visit, it's a coded diagnosis. That's what's sent off for billing, but that also tells you later why you're there. And then the other part of data in the EHR is qualitative. So these are data that are unstructured. These are all those clinical notes. And if you go to a teaching hospital, those may be notes from your medical student, your attending provider, your fellow physician, and even your resident physician, and they're all going to be about your treatment today. They also have all of the communications with you and any other side notes that may have been taken. So the answer is, there's a lot of data all the time. And so what I wanted to do was try to tie electronic health record data back in with big data. So I got really interested in when was the term big data defined. The answer is 1997 in NASA. And big data is just when data sets do not fit in main memory or when they don't fit even on the local disk. That's it. That's what started us down this whole big data set. And that's where our new term came from. So basically, they're extremely large data sets. And so I think the natural extension to that is the electronic health record big data. So we're one pediatric hospital with a catchment area that's roughly Cincinnati, Ohio. What's important about us is that we have about 1.3 million patient encounters annually, so they touch our hospital at any point in time. We have an EHR that was installed in 2009, and before that we actually had another one. So we've had this one about 10 years, and it has about 45 million individual patient encounters in it. This accounts for about 8 terabytes of data that we're storing around at the hospital that's both clinical data and research data. We are small when you compare us to something like Kaiser that might stretch across all of California. So the point is that electronic health records are big data, and there's a lot of it there to be used. So what can we do with big data in healthcare? So we just talked about that there are large amounts of patient data stored in EHRs. All of your visit data is always there for you to access again. And with the widespread digitalization of healthcare, so if you have a fitness tracker, if you have a heart rate monitor, there's the idea that all of these will come in and interact with your healthcare eventually to help guide your care. So there's an exponential amount of data continuing to increase and be added into the EHR that could help possibly make better decisions. So it's a potentially rich source for research and data mining. And what's one last thing is up to 80% of the data being stored in the electronic health record are unstructured. So in the terms of informatics, they're untapped. So what we have is just at our hospital more than 10 years of data, and no provider has time to go read through 10 years of patient notes or 20 or 30 before every single patient visit that comes in. What we want to do in the land of informatics is we want to help providers. So the fundamental theorem of informatics is that the computer and the provider together should be able to perform better than the provider alone. Are we ever going to replace providers with computers? No, I'm sorry. This is not the right conference for that, but it's not going to happen because we have a lot of different provider discussions that need to happen as time goes on. So I want to do a very brief overview about, because I'm academic, machine learning in the literature. So I did a search on PubMed in October for machine learning and medical informatics, and I got 8,324 hits. I'm not going to show you all of them. And then I said, you know what, let's see how much machine learning is being done in pediatrics, since that's my field. And I did the same search again, and I said machine learning in pediatrics, and I got 466 hits. So we have a long way to go. And there's a lot of machine learning being done in a lot of different places, but we have more we could do, and there's a lot of untapped things in pediatrics. So I'm going to talk about some of the things we've done at Cincinnati Children's, but we are by no means the only people doing pediatric research. So I wanted to make sure I highlighted some of the things that are happening in pediatric research that aren't just what I'm going to talk about today, which is epilepsy. And so this is a review. That's the idea here that I'm just trying to show you is that there's enough information out there to start doing review articles and start putting it all back together. In this paper, they focused on detecting sepsis in pediatrics, something that's also very challenging and not very well done all the time in adults because the data are very difficult to get to. This paper looked at children transferring in the pediatric intensive care unit. So these are the sickest patients in the hospital, and the idea here is exactly if we can predict who's going to transfer, maybe we can prevent it from happening. This one looks at predicting appendicitis when a patient comes into the emergency department. So if we predict who may come in with appendicitis, can we also start their care earlier and maybe reduce the number of appendices that we need to remove? And then what I'm going to focus on today is the work we've done on detecting patients with epilepsy who may be eligible for neurosurgical consultation and ultimately for neurosurgery. So I'm going to give just one slide of background on epilepsy. And the idea here is that epilepsy is one of the leading neurological disorders in the United States. There are more than 480,000 children who have epilepsy and more than 2 million adults. I think that most people probably have a little bit of experience and have at least heard of epilepsy, so I have a definition here for you. But basically, children, adults have seizures, and these can be controlled with medication and other treatment in most cases. 30% of epileptic patients are intractable, which means they're not well controlled with treatment. It also means that they've had at least 2 trials of appropriate anti-epileptic medications, and that those trials have failed to adequately control their seizures. So of the children who are intractable and eligible for neurosurgery, 55% to 59% of them are seizure-free after surgery. So it can be a life-changing, great experience for the correct kids. And of those, 77% report improved quality of life because they report improved seizures or decreased seizures. So we want to be able to find these kids. And the national average for pediatrics from time to diagnosis with epilepsy to being sent for neurosurgical evaluation is 8 years. The average in adults is 20 years, and the average for our patient population at Cincinnati Children's is 6 years. So what did we do? We developed a natural language processing algorithm, and these are going to be a lot of the papers that we have that came out about it, designed to identify patients who may be eligible for a neurosurgical consult. So Dr. John Pestian's lab sat down with neurosurgery, neurology, informatics, and computer science, and in a collaborative environment said, what can we do to help identify some of these patients? So they examined linguistic changes over time in epilepsy clinical progress notes. What's important in everything we talk about here is that it is entirely clinical progress notes alone. It is all unstructured. It is not structured data at all. So what they wanted to do was look at the linguistic changes over time in these progress notes and see if there's a change. Can we detect a change? Can we tell when a kid's going to be sent to surgery versus a kid who's never going to be sent to surgery? And so the long-term goal here is to reduce the time to initial surgery evaluation and hopefully send kids earlier. So what we did, and here's kind of the way it works for a child. Here across the bottom, years 1 to year 10, this is a child's disease progression with epilepsy. This purple line on top is a neurologist's language of intractable epilepsy. This blue line on the bottom is the neurologist's language of non-intractable epilepsy, and it's a natural progression that the neurologist is following for all of their patients as they treat them. Each of these little E's represents our patients' visits with the neurology clinics. So you can see that we start with the light blue E's, and the patient is non-intractable, so they are well controlled with medication, and they're doing a great job, and they are happy, and they have a good quality of life. And as this patient progresses in their care with their disease, they slowly move up to being intractable. At year 6, in their classic clinical care, they are sent for surgery, and their care progresses and moves on. But with the natural language processing we developed in the last slide, we can find these kids looking at all of our retrospective data 2 years earlier. So we could potentially send them 2 years earlier, and that's a big deal for a little kid. That's a big deal for all adults. So we did this, and we wanted to evaluate it prospectively. Like, how good of a job does it actually do when it's applied in the clinic on a day-to-day basis? So what we did was every week on Sunday night, we looked at all of our neurology patients who were coming in. We have about 6,000 visits a year. And we said, which of these children are coming in that may have intractable epilepsy? Which of these would we want to alert a provider and say, hey, have you thought about sending this kid for surgery evaluation? So we had 2 neurologists review all of the children that the system identified. So we knew that they were board certified. They would be the people the kids saw in the end anyway. And so what we see is that for these results, we did a pretty good job. 82% area under the curve. It looks pretty nice. We got a lot of kids identified that we may not have already seen. We have a pretty low positive predictive value, which seems kind of like a problem. And part of this is because when you look at the entire population of 6,000 kids, there aren't really that many that are surgery eligible. And at our institution, we do pretty close to about 50 surgeries a year, so it's not an exceedingly common thing to have done. And then the last thing I want to point out here is the number needed to screen is 3.6, or about 4. So what this means is that it's the number of people that need to be screened during our given duration or time to prevent 1 death or 1 adverse event. So basically, for every 4 people that we screen, 1 patient is definitely eligible for surgical consult and should be sent on to have a surgery workup. A surgery workup, by the way, takes somewhere from 3 to 6 months. So we are not rushing these children into surgery. We are saying, let's send you to some more experts and make sure you're really a great candidate for it. And an important thing about finding the children earlier is that for each year that someone is sent prior to surgery, if they are eligible, it's a 1.5% decrease in all-cause mortality. So in theory, we're helping these kids, giving them a better quality of life, and also decreasing mortality, which, as the informaticist, I think is a very fair trade-off for a handful of probably incorrect alerts. So let's talk about when we're wrong, because we're not always right. So here in the pie chart, 2/3 of the time, we're right. And the other third of the time, we're incorrect, and this child wasn't eligible for surgery. So part of what we asked the providers to do was say, of all these people who aren't eligible for surgery, why weren't they? Like, what can we do with those information? Some of these they wouldn't improve the quality of life. And so the algorithm isn't necessarily wrong here, but it's not something that a provider would do, and they wouldn't send them. Another one, it's unclear if the patient's actively having seizures. Again, data that can be collected during that day's visit that maybe they don't have. And so this is something that can feed into future algorithmic predictions the next time the patient comes in. Medical contraindications are an easy one for us to say we need to update our algorithm, we need to make sure patients who have these never get surgery referrals. And then there is always, here at the bottom, is the family declines surgery evaluation, which is social reasons, which are frequently not collected in electronic health records. So what can we do next with all these great data? Building the natural language processing isn't the end of development. Testing it without being in clinical care isn't the end of development. And so what we want to do is first improve the classifier. We can always make it better. And we did everything with unstructured data, but maybe adding structured data back in would really improve its performance some more. Another is to fully integrate it with clinical care, which we've done and is currently running. So provide those reminders, those alerts to the clinicians at the point of care and say, hey, have you talked about this with your patient? And if you don't want to, could you tell us why not? Another one is potentially to expand to other hospitals. We have data showing that looking at linguistics across pediatric hospitals, they match, so we'd be able to take our algorithm and port it somewhere else and get an even better data set to make better predictions. And the last one is to evaluate our algorithm. I think you're going to hear a lot more about this in the next talk, but I wanted to briefly address machine learning bias because I feel like this is kind of the elephant in the room in terms of machine learning. So what happens in the news is there are a lot of articles about why brand new machine learning applications have been scrapped because they're biased. And so this made us think, what if ours is biased? There's some known biases in epilepsy surgery referrals that are published in the literature. So the question is, why is an algorithm biased? Is it the underlying data? Could it be the algorithm itself? Could it be something else we haven't thought about? So what we wanted to do was evaluate ours because we don't want to be giving the providers any kind of biased information when it's something that we could discover, we could find, and that we could fix before we gave out those alerts and reminders. So we did a study and published it because we're academics. And so the question is our machine learning biased? The things that had a statistically significant effect on surgical candidacy scores were the distance traveled to our hospital, so the distance from their home to our hospital, whether or not the patient had public insurance. All children are covered by Medicare, so everyone at our hospital has insurance in a fashion, and age greater than 18 years of age. These all fit typical standard epilepsy referrals to a hospital. Patients who are older than 18 years of age probably have a lot of comorbid conditions and have been seen for other reasons as well. And the fact that they're still coming to a pediatric hospital suggests they may be sicker anyway. And then distance traveled, we're a specialty hospital, people get referred in, so people come in to see us. And so this is great news for us, but what about things that we're worried about? Race, gender, ethnicity, language, that might actually affect what providers are doing without realizing it. So things that had no statistically significant effect on surgical candidacy scores created by the algorithm were race, gender, and primary language. This is, again, great news for us, and while I think that there's always a chance for machine learning to be inherently biased, I think it's just as important to check it as you go to make sure that what you have is sound and is good. So what have we learned today? Or rather, what have I didactically shouted at you today? One of them is that we can improve pediatric care with unbiased machine learning algorithms. Another is that big data is here to stay because there's always going to be more information coming into the EHR, and there's always going to be additional information being brought in from other places. What I want you to go home with today is that healthy kids will lead to healthy adults. So if we do our work on the pediatric side, then we can create a better population as all of these children turn into adults. And what does the future hold for this research? So one of the things is that there's more opportunities for machine learning development and implementation. So again, as academics, we're always looking for collaborations. We would be happy to work with you, but a thing that's very important is that all I've presented here today is one disease in a very narrow field and doesn't even begin to touch everything that might be happening in healthcare that we could find using these data. But another thing that's very important to note is that looking across larger data sets and larger hospitals. So in the terms of epilepsy, there are so many adults who are also suffering with this disease, and we're only looking at 20% of the population. So if we expand to that other 80%, will our algorithm still work? Will we be able to find more patients and also give them an improved quality of life? We're looking at 20 years instead of 6 years, so maybe it'll be easier to find them earlier. And then the last thing is sharing data. So basically a learning health system. We want to take data, if we have everybody we could possibly have in the population, we would make a better inference and a better prediction. So in my last 30 seconds, what I want to do is thank everybody for coming, but I also want to point out that a very important thing in research is that research isn't possible without large, collaborative teams and institutions. There's no way to do research without a wide variety of people helping you out, without those working with you. John Pestian's been a valuable collaborator, without having support and without working with other people. And so all of those people are very important and should be thanked as well. Thank you.
Thank you very much, Judith. Okay, last but not least, we have Pietro Perona. And he's a colleague of mine from AWS and also the Alan E. Puck Professor of Electrical Engineering and Computation and Neural Systems with the California Institute of Technology. Pietro.
And thank you, Michelle. Thank you for inviting me. So I've been spending about 30 years in AI, starting with computer vision. And for most of my life, I've blissfully lived in the ivory tower of Caltech. My discipline was utterly useless. It was lots of dreams and hopes, but utterly useless. And in the last 5 years, instead, you've seen AI come on the stage. It has started being useful. And so I've got involved with Amazon, helping bring AI to the cloud. And also, I've realized that I have to broaden my perspective from the purely technical point of view of solving technical problems to the fact that now what I do is reaching society, it's affecting the life of people, and so I have to be concerned and I have to be mindful of how my craft is affecting the world. And so this is a completely new life for me, very interesting, lots of thinking, lots of talking to people who are different from me in different ways. And so I will share some thoughts with you tonight. It doesn't exhaust the topic, but I hope it's useful. So it's about machine learning in society, bias, fairness, and explainability. So in the last 3 or 4 years, we've seen a dramatic improvement in the quality of AI products. And I've seen at least 3 examples of situations where what we do is exceeding the ability of human experts. And so I have a few examples here. So the game of Go, as you know, board games are now already the territory of machines more than people. Medical diagnosis, you see some pictures of skin lesions, and I'll go deeper there. But in dermatology, there is one paper showing that a machine can do better than humans. Classification of animals and plants. If you can download the app called iNaturalist, where my students built a computer vision system that helps you recognize about 40 to 50,000 species of plants and animals. And again, no human can possibly do it. Then we have autonomous driving, not as good as human, but lots of hope to get there. Smart speakers, already very useful. Again, not as good as humans, but working hard to get there. So there is a lot of achievement and a lot of promise going forward. Now, how did we get there? I put a question mark near the I of AI. I'm not sure we have intelligence yet, and I'll show it to you in a moment, but certainly as an aspirational goal, it's there. And there are three legs to the stool. One is neuroscience that influenced the design of deep networks, and you know about deep networks. Of course, Moore's law that has given us GPUs that are powering our infrastructure. And on the right-hand side, it's large annotated data sets that were made possible by search engines and by Amazon Mechanical Turk, which was this very visionary project that Amazon ran about 10 years ago. And it allowed to create the data sets that nowadays we all use for annotating for training our algorithms. And Amazon is present in each one of these. And so, of course, we have computation and storage. We have SageMaker, and we have Ground Truth, of which I had the privilege of being involved with last year, deployed about 12 months ago, and it allows you to annotate very large data sets. Now, why can machines be better than humans? Why can we expect a lot from machines? And there are many reasons, and they are not all of them subtle. Some of them are pretty obvious. So one is almost cheating. When you drive a car, well, we're born as predators and manipulators. Our eyes are pointing forward. We don't have a good peripheral visual system. We're not like horses and rabbits. And so we have to retrofit the car with rear view mirrors in all positions and cameras and so on to back up. It's terrible. But if you have an autonomous vehicle, this is a Caltech vehicle that participated in the DARPA Grand Challenge 15 years ago, you can put sensors, as many as you want, wherever you want. It's obvious that machines have an advantage there. Another advantage, this is my son learning how to drive last year. And how does he learn? Well, by practicing. I tell him something, but then I let him do. And if he, touch wood, hasn't yet, if he has an accident, he will learn the hard way. Oh, I should have stopped a little bit earlier. I should have paid attention, all of that. So this is him learning. Now, for machines, it's completely different. It scales much better. This is from an accident that happened in autonomous driving a couple of years ago. And within days, all of the competitors in the industry had footage of what the vehicle saw before hitting the pedestrian. And there is a big analysis, and the whole fleet, not only within the same company, but across the industry, is benefiting from information that, of course, collected in a tragic way. But when something bad happens, you can benefit from it in a very scalable way. So that's another unfair advantage of machines. But for humans, we learn piecemeal, one at a time. And there is no way that if I have a car accident today, my uncle in Italy will drive better tomorrow. OK. Now, yeah, some people are laughing about Italian driving. I come from the north where we are very careful. So this is the skin lesion paper I was telling you about. And here is another big advantage of machines, which is they are much more easy than humans to benchmark. Here you see the blue curve is what the algorithm does. You have specificity and sensitivity. Specificity is how many do you, of the calls you make for taking out the lesion, how many are truly something that was cancerous. Sensitivity is how many of the cancerous ones will you detect. As you can see, the doctors and the machine are doing very well. They're very close to the top right corner. However, we can figure out the performance of a machine easily. We just feed images and we measure. For each one of the red dots, which are the doctors that were tested, it's a piece of work, right? It's imagine getting some busy doctor into an office and asking them to click on images. And chances are that your dermatologist, certainly not mine, I ask him, they don't get benchmarked. So when we go in, what is their trade-off between sensitivity and specificity? I don't know, right? And each one of us may have different needs. So there are two lessons from here. One is machines are easy to benchmark, so you know what you get. while humans are humans. And the second one is, in principle, you can tune a machine to match your need, between risk-taking and wanting to get some piece of skin taken off your body. So that's another advantage of machines with respect to humans. Now, machines also have challenges where you clearly see that humans are still better. And so we shouldn't be too cocky. So one is the efficiency of learning. Each one of the examples I gave you requires an enormous amount of training examples. My back-of-envelope calculation in the situations I've been involved with is about 100-fold more training images for a machine than for an equivalent human to achieve the same level of proficiency. So it's a lot. Now, luckily, we have huge training sets. And for example, in dermatology, you could beat the humans, but it's very expensive. So that's one drawback. Second one is the ability to generalize. So here you see 3 images I took from the web, and I fed them into a popular online image recognition algorithm that gave me a bunch of labels. And you can see that the algorithm is doing great, right? Read all the labels. They all reflect well what is there in the image. It's doing a great job. Unfortunately, I know how it's built, so I can cheat it, I can fool it. And here is what happens if I go and pick pictures of cows on the beach, which is not a common place where you see cows. And here, the algorithm is in trouble. So what happened? Well, what happened is that the algorithm is learning everything about those pictures, not just a cow. It doesn't know that there is a cow there. It just knows there is some bunch of texture that people happen to get excited and call cow. And now I change the texture around and things are going south. Okay? So I think a couple of the previous speakers pointed this out. When you stay within the domain, when you do the training, usually you're doing well because you have lots of images to train and test. And you can benchmark, so you get some confidence. But if you go outside of the domain, then all bets are off. And so you need to be very careful, and machines don't generalize well. Okay. Last one, I want to point out, there are some more. A theory of mind, here I stopped because I saw an elk, and I stopped also because I was interested in the elk, but also because I knew that the elk is a somewhat touchy animal. I don't want to get too close. I want to let him move on, so I'm watching his body language, and as soon as I feel like he's calm and not paying attention to me, I will drive behind him. That's not true for today autonomous vehicles. They don't have a theory of mind, and so this absence of social ability is a problem on which the car driving companies are working, okay? So thinking of other things out there as beings who have plans and desires and wishes and can socialize with us rather than just as obstacles is a key step to being successful. So just to summarize, these are, I'll skip it because I made the point, these are the advantages of machines on the left and humans on the right. Now we get to the meat of the story. As we bring machines into society, machines more and more interact with humans. So it's not just about advertising some product on a web page. It's truly about dealing with humans in fairly sophisticated and touchy situations. And we saw uses in medicine just a moment ago. And so what do we ask from machines when they interact with us? Okay, it's vital that they are successful interacting with us because we are so valuable. And so certainly they have to be safe. That's number one, always safe. They have to be useful, do something that we're willing to pay for. But then also they have to be friendly, which means considerate, respectful, acknowledge our feelings, be aware of the emotional and social situation, and trustworthy, namely what they promise to do, they have to deliver, and we have to be able to look inside the box and gain confidence that what the machine is doing is something that is going to end up in something that we consider good. So we have to have trust in the machine to allow it to operate and to interact with us. And if you think what I listed here is 4 properties that are being taught to young children when they go to the kindergarten. The first 2 years, 98% of the time is safe, don't push, don't bite, be useful, help clean the classroom, help your parents at home, be friendly, so be aware of other people's emotions, don't insult your friends, don't call them names. Trustworthy, if you're engaged in a job in something, explain what you're going to do, explain how it's going to end up, demonstrate it, how to carry it out and all of that. Okay, so this is what we want. And if we, so what's the reason to bring machines into contact with humans? Well, first of all, the two things that come to mind every time are, they're inexpensive, they're scalable, they can do a lot of work, so that we heard before, they don't fall asleep and all of that. But it turns out that those two last properties of being friendly and trustworthy are also something that machines can help achieve in society. So we have to be aware that society is not perfect, and often the reason to bring a machine into the picture is to improve how society treats individuals. And we saw the case of medicine epilepsy. The machine is helping avoid unnecessary surgery on kids and so on, avoid mistakes, all of those things. So I want first to survey briefly a few failures of society as it is, when it's manned by people, as it were, so that it gives us a little bit of a baseline on where we bring machines, what are we trying to do. So, this was in the LA Times a week ago, a case where twins arrive at the border, file for asylum. One is taken in, one is sent back. What happened, nobody knows, but that's very annoying, to say the least. Now, it's not that there are bad people there in the bureaucracy, and so I was digging through the literature. There is this nice article in The Atlantic about how bureaucracy works and why do bureaucrats don't care. Well, somebody went behind the lines and worked in an office helping people get support from the government, and realized that, the bureaucrats look always somewhat pitiless and rule-following, but truly they're put in front of very difficult situations. There are too many rules, they're ambiguous, you have to work out some solution, and the cases in front of you are complicated, and there is a lot of work to be done sometimes, and you don't have the time to do it. So typical situations where you think, all of us in the room think machines would probably be able to help in some form or another. Sometimes humans are devious on purpose. So this is one famous case, and it's still haunting us today. So everybody would agree on what the rules for making districts should be, namely neighbors should vote with neighbors, so the boundaries should be fairly short and the districts compact, but as soon as you put somebody in charge, that person will have a whole set of ideas that go beyond that. So there's another problem in society that people will be devious, and it's very difficult to monitor or benchmark their actions or keep them in check. Another one is genuine mistakes. So this is a sad story of this lady who was assaulted. She pointed to a person in a police lineup. It turned out it was the wrong person, but it took 20 years of him being in jail before it came out. And when this was clarified, she was, of course, very sorry. She went to him. They formed a team to go around the country and proselytize about how police lineup should be carried out. So the story ends very well, but it's clearly a problem. And again, it's not that she was trying to frame someone. It's just that the human brain is not very good at doing this task. Okay, and so humans are sometimes overly confident, but there are experiments that show that, at 4% false match rate, you still have maybe only 30% of correct match rate. So it's a very faulty system. And on top of that, the signal in your brain is strongly biased. And we saw about bias just a moment ago in the pediatrics talk. And here are researchers at Stanford who test African Americans and European Americans in recognizing the faces of individuals of the same or the other ethnic background. And so the top plots show you that there are big differences in the performance. Namely, you're much better at recognizing people that belong to your group than other groups. And the bottom plots show you that the signal in the brain while you engage in this task is very different depending on whether you look at somebody who belongs to your group or not. So it's truly nothing to do with bad will or or being nasty, but it has to do with the fact that simply you don't have enough training sometimes, okay? So humans have the same problem as a machine. If you don't train them enough, they don't do well. And you can go to this website, implicit.harvard.edu, to measure your implicit biases, and you will be humbled by the fact that you think you have no bias at all, no racial bias, no sex bias, and so on, and in fact, it may turn out that you do. And so this is data from tens of thousands of people who take the test, and you see that many people associate females with liberal arts and males with science. That's the pink stripes. Many people have the opposite, but fewer bias, and the only unbiased people are about 20%, right? So you have only 20% of the population is unbiased somehow in this particular task, which it makes you worried. So this is the picture of the society we live in. It's full of mistakes, biases, somewhat trickery sometimes, and our job as people who build AI is to help make the world a better place. That's what engineers want to do, and what do we do? How do we come in, and how do we help, and what are the targets? So, of course, we all want to have a just society, and the Statue of Justice always has these scales, even weights on both sides, and so that's a very important thing. And so the idea would be that maybe human justices, human doctors, and so on could be helped by our creators, our creations, AI and data analysis and all of that. And so now, one place that I think is very clear, there is not even AI here, but one place where I can make it very crisp is this example. On top, you have the districts in North Carolina drawn by humans, and there is gerrymandering galore, like to our eyes, it's clear. On the bottom, it's an algorithm that draws districts by minimizing the length of the boundaries. Now, if you take people from any party, you put them around the table, and you have a discussion, and you ask them, so you take away the label North Carolina. You say, well, this is a state. Now, which one is the right way to draw districts? The discussion will last 3 minutes, probably. They will all agree, okay, this, of course, the bottom one is the right one. So this is the case in which you see exactly where you draw the boundary between human and machine domain. The humans are in charge of deciding what is fair, what they want, which is we want districts where neighbors vote with neighbors. It's a purely human decision. There is nothing mathematical behind it. It's just the society we want to live in. And now the machine is put in charge of implementing the choice of humans. And since the machine can be benchmarked, it can be certified, it can be inspected by anybody, you eliminate all the aspects of chicanery and trickery behind the scenes, because everybody will agree that this is the fair way to go about it, and you just let machine do it. While nobody would want a human to do it, because you know that a human will try to do something a little bit different, okay? So this helps me draw this line, and we'll see it later. Now, this is on face recognition. What can machines do? And so again, we have good news. This is a study that came out 2 years ago, or last year, in fact, by Alice O'Toole from U Texas and other people. And they looked at how good are people at recognizing individuals. So we go back to the case of the cotton case. And you see on the right, it's algorithms. And high is good on the scale, so towards the high is perfect. And the dots, the lozenges, are algorithms in 2015, 16, 17, and 17. And you see that the progress has been quite fast. On the left, you have examiners from police forces, and they are trained specifically for doing this job. And you see two things. There are some who are really good at the top, but you also see that there are quite a few who are quite terrible. And you don't know which one is which, right? You go to a random police force. Who knows if they know if they have a proper examiner or not? And the average of the examiner is not as good as the machine. And in the middle, you have regular people, students from a campus, and they're not good at all. So that shows you that training counts for a lot here, and human experts are there for a reason. So here, machines give a lot of value, and the authors of the study conclude if you want to have a good system, you must have a machine in place. And then it should be helped by a human, because you also want a human to finally give a final judgment. At least eliminate all the errors and make sure that the machine is there to give you a safety net. This is another piece of good news. This is the NIST, which is our National Institute of Standards and Technology. And the NIST, unbeknownst to most of us, has started a few years ago a very rigorous program for benchmarking algorithms for face recognition. Again, they recognize that this is a very important technology that has effects in society and in many different branches of commerce. So every 6 months, they come out with a 300-page report that tells you for all the vendors that are there, and there are hundreds of vendors, how well do they perform. And as of a couple of months ago, they started putting out charts that also look at bias, namely, is there bias between men, women, African Americans, or Caucasians? And hopefully they will put in more ethnic groups as time goes by. And again, it's the usual limit is being able to collect good data sets. And so here you see that there is some bias, but fairly small. And the good news is African American males, which are a sensitive category, as you will see in a moment, perform better by an order of magnitude. So the false match rate is 10 times less, at least in this experiment with this data set. So the good news is there is somebody watching, and somebody is measuring bias, and slowly we are building transparency and trust through being able to measure. And so at some point, we will flip around and we will stop trusting humans, and I think we'll start trusting machines and things like that, because we'll have numbers. Well, for humans, we don't have numbers, right? So, okay, that's good news. Now, machines have bias, as we saw before, and so it's very important as we build machine, and so this is my job, is to think about where is the bias coming from, apart from measuring it. How can we improve the situation? And so let's look at a few situations. One is fairly obvious, is the amount of training data. So here, this is data from one of my students, Sarah Beatty. She works on wild cams that take pictures of wild animals in the southwest of the US and in the Serengeti in Africa, and classifies every animal by the species, and this is helpful for managing wildlife. And what you see here is that in the southwest of the US, there are very few badgers. That's the animal in the top left. And so only 5 training examples. So the error rate is 80%. While there are lots of opossums, about 3,000 in the training set, and so their error rate is 2%. Okay, so if you are an opossum, you feel like the system is fantastic. If you're a badger, you say, I don't agree. I don't think nobody should use it because it's terrible. And so how do you fix this? I mean, society is a long-tail distribution. We are, if you divide us up into groups, there are some groups that are very small and some are very big. And so this will happen. So what do you do, right? And the way to do it is to invest and to be mindful and to think that there are people who have fewer training examples, and you try to collect more in that category, and you try to do a good job, and you try to improve also the technology so that the systems become more efficient in learning. But this is certainly something to watch for. Now, some classes are easier. Prickly pear is very easy. Prairie lizard, there are something like 10 species of lizard that look all the same to me, and so it's very difficult to make them out, and so you need lots of training examples. Now, there are funky correlations. So here we've seen deep fakes before, so these are synthetically generated faces. And what we're trying here to do is to generate a face that is in between male and female. You see it in the center of each strip, and then push towards male and push towards female on the 2 sides, okay? So why do we do that? Let's not get into that for this talk, but what you see here is that there are some correlations. So the most obvious one is females tend to have long hair, and males tend to have short hair and a beard, right? So it's not necessary to be a man to have a beard or to have short hair, but most of them are that way. Now, another funky correlation that you see is that females are younger and males are older. So why would that be? Well, because in the popular training sets you find, which are taken from celebrities, women reach starhood earlier than men. So there are more young women and more middle-aged men in these data sets, and so the data sets are biased in this way, which is revealed by this exercise. A third one is females smiling more and males smiling less. Why? I don't know. It's not that I'm unable to smile, but that's what you find. And so this sets your brain in motion. If you train your systems with these data sets, there may be some unwanted consequences that we have to be aware of. And so how do we measure, how do we discover these correlations? So it's lots of hard work that you have to put into it. But of course, the advantage is as soon as you figure it out, you can correct it, unlike humans. And so we go back to the old lesson that machines are scalable in their learning. Now, as we saw, females tend to have longer hair, males shorter hair. So you have very few males with long hair, very few females with short hair in the training sets. And so if you look at gender classification, it's more or less fine when hair length is normal. But when hair length is atypical, then you have mistakes. Now, it turns out there are very few males walking around with the hairdo you see on the right. You don't see almost anyone at this conference, and very few females on the left. Okay? Now, the question is this okay? Or should we work hard? Is the next investment to improve this aspect? And so it's up for us as society to decide where we use money and what do we care about. Do we care about children with epilepsy, or do we care about this or anything else? And so it's a question. Now, the last hard nut is that there are very different definitions of fairness, and we should be aware of that. So while bias is something we can measure, fairness is in the eye of the beholder. It's something that we hold deeply, but it's a construct. And so let me show you an example of this. It came out, it's a fairly well-known case. It came out in the press 3 years ago. Somebody analyzed, so there is an automated system for assessing whether someone who is in jail should be released early, given parole. And the way this is done is normally there is a 3-member parole board, and they talk about it and they decide whether to let a person out. Now, it turns out parole boards are somewhat inscrutable, and most prisoners say, I have no clue what they will do with me, and I have no way of controlling it, and they feel very frustrated. So enter AI, people analyze the data, and they try to predict from the CV of a prisoner whether they will reoffend or not. And so there is a machine that does it, a piece of software. So somebody analyzed the data and realized that if you waited 2 years and you looked at what happened when people were left out of jail, and you look at people who had not reoffended, namely the good people who should have been left out, well, amongst the whites, only 25% had been labeled high risk, namely being kept behind. But amongst the African Americans, half. Namely, half of the people who would not have done damage were kept in jail. That sounds very unfair, and it's different between the two ethnic groups, so it's very bad. And the opposite happens if you take the people who do commit a crime again, right? So this is heart-wrenching, and in the press, people came out very strongly saying we should stop this whole software thing, this whole AI thing. Now, the data was examined a couple of years later by a statistician at CMU, Alexandra Cholechova, and she plotted it in a different way. She said, well, let's take the score that the algorithm gives to these prisoners, and let's see if the score, which is predictive of whether they will offend, if the score is biased. And she finds that it's not biased at all. So that if you get a 10, you're equally likely to reoffend if you're white or African American, and vice versa. And also if you get a 4 or a 3, your background, your ethnic background is not influencing the choice. So how is this possible that on one side it's completely unfair and on the other side it's perfectly fair? And the fact is that we are conditioning on two different things. Above, we condition on what happens afterwards, and below, we condition on the score. And since the two populations are very different, the distribution of scores, then you will get different results. So let me use an animation to go through this again. And so here I will use women and men. Women are light, men are darker. And again, we have a population of 18 people, 9 women, 9 men. And we are assessing their risk. And so we find that 9 people got low risk, 0. 9 people got high risk, 1. And it's well known that men tend to be more, end up more in jail. And so it's not surprising that more men got a 1 than women. And then we wait to see what happens. And we see that the algorithm predicted things in a fair way, in the sense that on the left, 1/3 of the men got unreasonably left out of jail, but reoffended, and 1/3 of the women also. And on the right, it's 2/3 of the men and 2/3 of the women got kept in jail. So the system seems to have done a fair job. Women and men were treated fairly. It had only to do with their likelihood to reoffend. Now, you can rearrange these, and I didn't change anything. I just rearranged them into who offended and who didn't, not by the scores. And now if we count, you see that we get the unfair reading. So 4 of the men, or half of the men who did not reoffend got dinged, and only 1/5 of the women. So it's very unfair towards the men. Okay? So now you saw that depending on which criterion of fairness we use, whether we use the prior, namely, let's see what the score is, and let's go for the decision of the score, then there is no problem at all. That's what you have upstairs. While if we go to what happens afterwards, namely, we divide people depending on what they did afterwards, we get a completely different picture. Okay? So this says the fairness, you have to be very careful because you have different criteria of fairness, and logical people will disagree. And it turns out you can only have one fairness criterion satisfied at a time. You cannot have many different ones satisfied at a time. And so it's very important that society discusses this and that politicians vote and that we have a human-made decision here. There's no role for machines in this. Machines then can act upon it, but the foundation, namely what should happen, should be in the hand of humans. Okay, last thing I want to talk about is explainability. And it's very important for us to know why a decision was made. And recently, many of your companies had to deal with the European Union, who was particularly vociferous about it and decided that you have to provide, so anyone who is the object of a decision should be given a reasonable explanation and so on. And so, so let's look at 3 cases and let's pit machines against humans. Let's see who wins. Parole cases. And so it turns out that, again, as I was saying before, prisoners complain that parole boards are inscrutable. There is a computer scientist from Duke, Cynthia Rudin, and her team looked at the same data that we talked about before, the prisoners, and synthesized the simplest possible set of rules using machine learning, simplest possible set of rules that give you the same performance as the best possible classifier. And as you can see, out of about 125 features that you can look at in the records of a prisoner, she said only 3 matter, really. It's age, sex, and prior offenses. And here is the rule. If age is 18 or 20 and the sex is male, then keep them behind bar, no matter what. You know, if young males, just keep them behind bar. Which, you know, sounds like it matches your intuition. By the way, I have teenage children, so I'm a little bit worried. So if age is 21, 22, and there are prior offenses, then keep them in jail. If prior offenses are more than 3, then sorry. Otherwise, let them go. So here, I feel AI has done a good job. It's a bit of luck that Cynthia has this method for synthesizing very simple classifier. It turned out it worked this way. And now, if I were a prisoner and would have to choose between a parole board or Cynthia's rules, I would say I go with Cynthia's rule. At least I know what's going to happen, right? So this is one case where I think machines are doing better than human. And I know I'm not an expert, so don't take my word. Just do your reading. And driving, something that we do every day. On the strategy part, you know, which itinerary do we take? This is me going from Pasadena to UCLA. I find that machines are superior. If you get onto a taxi, you say, which way will you go? Well, you know, I'll take 405. Why? Well, you know, at this time, probably, blah, blah, blah. Not terribly convincing. Well, the machine gives you a perfect map with all the traffic and so on, you trust it. On the tactics, you know, I stop because there is a red light, there is a pedestrian. Both machines and humans have the same token. They all pay attention to the same things. They're able to verbalize them the same way. I think that there is a tie there. A third case, so this is explaining what is there in a picture. Machines are still not doing very well. Humans can answer almost any question. They can motivate it and so on. I feel like here, humans are far superior in explaining the content of a picture, or why something happened from a single picture and so on. So there are many cases in which humans are far superior to machines. So I think that you can go either way, and certainly my field is working really hard to improve explainability, and so here again I'm somewhat optimistic that with time we'll see more and more progress. Okay, so just to summarize, what are the advantages of machines and people? So improving at scale, certainly machines are much, much better than people. Explainability, both sides are to be improved, but certainly machines can improve more in some sense than people. I'm optimistic. What's easier to regulate? I think it's easier to regulate machines. You can audit the software, you can benchmark them, and you can put very stringent laws on people. People are squishy, they're difficult to regulate sometimes. But who can define what is fair and what is unfair? Well, certainly that's the job of people. And so this somehow gives us a sense for what are the boundaries between things that we should expect in the future. And so the last, where am I with my outlook? And so you hear people saying AI is magic or AI is dangerous, you should avoid it, and so on. So these are all oversimplified statements. What I can say is AI is useful and handle with care, work on it, and things will hopefully improve a lot, but always keep your eyes open. And so my current position is this one. Okay, thank you.
Thank you. Fantastic talk, Pietro. Thank you so much. Well, that brings us to the end. I hope you learned a lot, and I hope you are ready and inspired to go out and build with some machine learning. So please check our lineup of additional machine learning solutions throughout this conference, from Deep Racer to SageMaker to Frameworks, and our other AI services. And don't forget, if you enjoyed this afternoon's program, please go to our app and complete the survey on our mobile app. Is there one more slide? Nope. Go to the app and complete the survey. So thank you so much. This concludes the Machine Learning Summit for 2019. Thank you.